What if everything you thought you knew about time was just a small part of a much larger, more mysterious picture? We often imagine time as a straight line, a constant, predictable flow from past to present to future. But across the cosmos, in places where gravity bends the rules and quantum physics takes over, time behaves in ways that defy our everyday understanding. It doesn't just march forward, it twists, loops, folds, and even knots itself into patterns that are as beautiful as they are bewildering. This isn't science fiction. It's the reality that physicists and astronomers are uncovering as they explore the deepest structures of the universe. And it's a story that changes not only how we see the cosmos, but how we see ourselves within it. Today, we're setting out on a journey to 25 extraordinary places where time isn't linear, it's woven. Like an intricate tapestry, time in these regions intertwines with space, gravity, and energy in ways that challenge our most fundamental ideas about cause and effect, memory, and even reality itself. From the very edge of a black hole's event horizon where time appears to stand still, to the seething quantum foam at the smallest scales of existence, we'll travel through realms where the familiar arrow of time bends, branches, and sometimes even doubles back on itself. These are not abstract mathematical curiosities. They are real physical locations or states of the universe that push the limits of what's possible and invite us to rethink everything. By the end of our exploration, you won't just have a list of cosmic wonders. You'll have a new lens through which to view the universe. You'll understand why some of the greatest scientific minds believe time itself may be an illusion, a side effect of our limited perception in an infinitely more complex reality. And you'll see how these ideas don't just live in textbooks. They shape technology, inspire philosophy, and touch on profound questions about existence and consciousness. So settle in, open your mind, and get ready to see time not as a river flowing in one direction, but as a vast, shimmering fabric rich with pattern, riddled with mystery, and far more incredible than you ever imagined. But to truly grasp the idea of woven time, we first need to re-examine our most basic assumptions about what time even is. For centuries, the view established by Isaac Newton dominated our thinking. Time was absolute, universal, and relentless. It was a master clock ticking away at the same steady rate for everyone and everything, everywhere in the universe. This linear, one-way flow from past to future felt like simple common sense, an immutable backdrop against which the drama of existence played out. Yet this comforting notion of a single, universal now was completely shattered in the early 20th century by a young patent clerk named Albert Einstein. His theory of relativity introduced a radical new concept, that time is not separate from space, but woven together with it into a single fabric, spacetime. And this fabric is not rigid and static, it's dynamic and malleable. It can be stretched, compressed, and warped by mass and energy. This means that a clock in a strong gravitational field, like here on Earth's surface, will actually tick more slowly than a clock on a satellite orbiting high above us. This isn't a mechanical error, it's a fundamental property of the universe. Time itself is running slower down here. Similarly, if you were to travel at an immense fraction of the speed of light, time for you would dilate, meaning you could journey for what feels like a few years and return to find that decades or even centuries had passed back on Earth. Your personal thread of time would have been stretched thin compared to everyone else's. Just as we were coming to terms with this bizarre, relative nature of time, quantum mechanics entered the picture and made things even stranger. At the subatomic level, the clear, predictable flow of time seems to break down entirely. Particles can exist in multiple states at once, and events don't have a definite order until they are observed. Some interpretations suggest that time might not be a fundamental ingredient of reality at all, but rather an emergent property that arises from the complex interactions of countless quantum particles, a collective illusion of order born from underlying chaos. Think of it like the temperature of a gas. A single molecule doesn't have a temperature. Temperature is a property that only emerges from the collective jostling of trillions of molecules. In the same way, physicists like Carlo Rovelli propose that our experience of time flowing in one direction may be a similar kind of emergent phenomenon, a story our brains tell us to make sense of a world where the fundamental laws of physics are, for the most part, timeless. This profound shift in thinking from time as a master clock to time as a flexible dimension, and perhaps even to time as an illusion, is the essential foundation for our journey. It prepares us to visit places in the cosmos where these wild theories are not just abstract math, but the concrete, observable rules of reality. Now, let's journey to our first destination, a place that has captivated and terrified the human imagination in equal measure, the event horizon of a black hole. Picture yourself as a brave astronaut on a one-way mission, piloting your ship toward one of the universe's most mysterious boundaries. As you approach, the black hole itself may not look like much more than a perfect circle of utter blackness, a hole punched out of the starfield behind it. But this darkness is deceptive. It's not an object, but a threshold, the point of no return known as the event horizon. This is where the true weirdness of woven time begins to reveal itself in the most dramatic fashion imaginable. From the perspective of mission control back on Earth, watching your voyage through powerful telescopes, something profoundly strange would happen as you crossed this invisible line. To them, you would appear to slow down. Your movements would become more and more sluggish, like a video played in extreme slow motion. As you inched closer to the event horizon, you would seem to freeze completely, your image becoming redder and dimmer until you essentially faded from view, forever suspended in time at the very edge. It's as if the universe itself has pressed pause on your existence. This isn't a trick of the light or a camera malfunction. It's a direct consequence of Einstein's general relativity. The gravitational pull is so unimaginably strong here that it warps the fabric of spacetime itself, stretching time out to infinity from an outside point of view. A single second for you could equate to thousands of years for everyone else. But here's where it gets even more mind-bending. For you, the astronaut actually crossing the horizon, none of this slow-motion drama would be apparent. From your own local perspective, time would feel perfectly normal. You wouldn't see a vast, scary void. You would simply cross the boundary without any sudden jolt or dramatic event, at least initially. If the black hole was large enough, you might not even know the precise moment you passed the point of no return. The problem is, you couldn't turn around and report this back. Once across, every possible path forward leads inexorably downward toward the central singularity. The pull of gravity would become so intense and so different between your head and your feet that you would be stretched into a long, thin stream of atoms in a process vividly known as spaghettification. So while your personal timeline continues forward, the universe's timeline effectively writes you out of its history the moment you cross the horizon. This bizarre disconnect between perspectives lies at the heart of a major puzzle in physics called the black hole information paradox, famously wrestled with by Stephen Hawking. He realized that if things can only fall in and never come out, then information about those things is permanently lost from our universe. This violates a core principle of quantum mechanics, which states that information must always be preserved. Hawking's revolutionary solution was to propose that black holes aren't completely black. Due to weird quantum fluctuations at the very edge of the event horizon, pairs of virtual particles can pop into existence. One particle falls in while the other escapes as a faint whisper of radiation, now known as Hawking radiation. This slow leak of energy means black holes eventually evaporate over astronomical timescales. But the question of what happens to the information contained in the things that fell in remains one of the most heated debates in theoretical physics. Does it get encoded in the radiation? Is it lost in a separate universe? The event horizon is where this battle between the deterministic world of gravity and the probabilistic world of quantum mechanics plays out, making it the ultimate cosmic laboratory for testing the limits of our understanding and showing us that at its most extreme, time doesn't flow, it shatters. But if crossing the event horizon feels like a one-way trip into a frozen moment, then what lies beyond it makes that seem almost simple by comparison. Our journey now takes us deeper, past that point of no return and into the heart of the darkness itself, toward the enigmatic and terrifying core of a black hole known as the Singularity. This is not a place you could ever visit and hope to describe, for it represents the ultimate breakdown of reality as we understand it. While the event horizon warps time to an extreme degree, the Singularity is where the very concepts of time and space unravel completely. Imagine that same brave astronaut having survived the crossing of the event horizon. Despite the immense tidal forces beginning to pull at their ship, they are now irrevocably drawn inward. According to the equations of general relativity, every path forward leads to a single point at the very center, a point of zero volume and infinite density. This is the Singularity. Here, the curvature of spacetime predicted by Einstein's theory becomes infinite. All the mass of the collapsed star and everything that ever fell into the black hole is crushed into an infinitely small speck. In this state, the familiar rules of physics simply cease to function. The tools we use to describe the universe, forces, particles, even the dimensions of space and time lose all meaning. It's not just that time is distorted. At the Singularity, time as a distinct concept stops existing altogether. Think of spacetime not as a static stage but as a flexible fabric. A planet creates a gentle dip in that fabric, like a bowling ball resting on a stretched sheet. A black hole, however, doesn't just make a dip, it pulls the fabric into an infinitely deep, infinitely narrow needle-like point. At that needle's tip, the fabric isn't just curved, it's torn. In this unimaginable state, the separate threads of space and time are no longer woven together into a coherent tapestry. They are fused into a single, indecipherable knot where the words here and now have no distinction. This is why physicists often say that at the Singularity, time and space swap roles. Outside the black hole, you are free to move through space in any direction, but you are always forced forward in time. Inside, falling toward the Singularity, moving through space is no longer optional. You are relentlessly pulled toward the center. But some interpretations suggest that in this bizarre realm, time itself might become a dimension you could potentially move through, blurring the line between your past and your future in ways that defy all logic. Naturally, the idea of a true infinity in nature makes physicists deeply uncomfortable. Infinities in our equations are usually a sign that our theory is incomplete, that we're missing a crucial piece of the puzzle. This is where modern theories of quantum gravity step in, attempting to sew the torn fabric of spacetime back together with a new understanding. One leading idea, called loop quantum gravity, proposes that spacetime isn't smooth and continuous down to the smallest scales. Instead, it might be made of tiny, discrete, indivisible units, a kind of pixelated structure of reality. Think of it like a digital photograph. If you zoom in closely enough on a digital image, you'll see it's made of individual pixels. Zoom in on the universe according to this theory, and you'd find the fabric of reality is woven from tiny, finite loops. This has a profound implication for the singularity. It can't be infinitely small. There is a smallest possible size, so rather than collapsing to an infinite point, the core of a black hole would reach a maximum density and then do something else. Perhaps it would rebound or transition into something new, avoiding the catastrophic breakdown of physics altogether. This suggests that at the most fundamental level, time itself might not be a continuous flow, but might instead advance in tiny, discrete steps, like the ticking of a cosmic clock, but with each tick being an unimaginably short unit of time known as the Planck time. This radical rethinking challenges our most basic intuition about cause and effect. Our entire experience of reality is built on the principle that causes happen before their effects. But in the quantum foam near where a singularity would be, this sequence could break down. The extreme conditions could allow for closed time-like curves, where an effect could loop back and become its own cause, or where the past and future could overlap and influence each other. It's a domain where the words before and after might lose their anchor, presenting a profound puzzle that pushes the limits of not just physics, but philosophy itself. Yet if the crushing finality of a singularity represents one extreme of cosmic architecture, the concept of a wormhole offers a far more dynamic and connective vision of the universe's hidden plumbing. Often depicted in science fiction as a shimmering tunnel through the stars, a wormhole, or an Einstein-Rosen bridge, is a theoretical shortcut through the very fabric of spacetime itself. Imagine the universe is not a flat sheet but the surface of an apple. An ant walking along the curved surface has a long journey from one side to the other. But if a worm bores a tunnel directly through the apple's core, the ant can take a drastically shorter path. A wormhole proposes a similar tunnel through the higher dimensions of spacetime, connecting two distant points that would otherwise be impossibly far apart. This isn't just about shortening a space journey, it's about fundamentally rewiring our understanding of distance and duration. The mathematics behind this incredible idea are firmly rooted in Einstein's theory of general relativity. In 1935, Albert Einstein and his colleague Nathan Rosen found that by solving the equations for a black hole, they could describe it not as a dead end, but as a bridge to another region of space and time, a white hole, erupting with energy elsewhere in the cosmos. This initial concept, the Einstein-Rosen bridge, was a purely mathematical curiosity, a structure that would form and then pinch off instantly, far too quickly for anything to ever traverse it. It was a fascinating idea with no practical application, a beautiful ghost in the machine of physics equations. For decades, it remained a niche footnote, a tantalizing hint that the universe's rulebook might contain passages about connectivity that we had simply not learned how to read. The modern reimagining of wormholes, and the one that captures our imagination, is largely thanks to the work of physicists like Kip Thorne. He and others began to ask a revolutionary question: could such a bridge be held open? Could a wormhole be made stable and traversable? The answer, it turns out, might be yes, but at a truly fantastic cost. Keeping a wormhole from collapsing would require a substance with negative energy density, often called exotic matter. This isn't antimatter. Antimatter has positive energy. Exotic matter would have a kind of anti-gravity effect, repelling rather than attracting, and it would need to be threaded through the tunnel to prop it open against the immense forces trying to slam it shut. While we have glimpsed tiny, microscopic effects akin to negative energy in quantum experiments like the Casimir Effect, The sheer amount needed to stabilize a human-sized wormhole is far beyond anything we can currently conceive of creating. It's a breathtaking theoretical possibility that remains, for now, firmly in the realm of profound speculation. The most staggering implication of a stable wormhole isn't just spatial travel, it's time travel. Because spacetime is a single intertwined entity, a shortcut through space is also inevitably a shortcut through time. If one end of the wormhole was taken for a high-speed joyride near the speed of light and then brought back, time dilation would mean that end had aged less than the stationary end. These two mouths of the same wormhole would then be out of sync, not just in location but in time. Walking into the moved mouth might lead you to exit the stationary mouth in its own past. This creates what physicists call a closed time-like curve, a path through the universe that loops back on itself, allowing a particle, or potentially a person, to return to their own starting point in both space and time. This is the mechanism that could make time travel to the past a physical possibility, not just a fantasy. Naturally, this leads directly to the famous time travel paradoxes. What if you went back and prevented your own birth? The existence of such paradoxes leads many, including Stephen Hawking with his chronology protection conjecture, to believe that the laws of physics will always conspire to prevent stable wormholes from forming, perhaps through explosive quantum feedback that destroys the tunnel the moment it becomes a time machine. Yet other theories, like the many worlds interpretation of quantum mechanics, offer a way out. In this view, traveling through a wormhole to the past wouldn't change your own timeline. Instead, it would branch you off into a new, parallel universe where your actions create a new future, leaving your original history intact. The wormhole, then, wouldn't just be a tunnel through our universe, but a gateway to an entire multiverse, weaving together not just moments in time, but entire alternate realities. It transforms the concept from a simple shortcut into a cosmic loom, intertwining the threads of cause and effect across a breathtaking tapestry of possibilities. But if the mind-bending physics of black holes and wormholes feels like exploring the strange back alleys of the cosmos, our next destination takes us back to the very beginning of everything, to a moment of such profound and violent creativity that it set the entire stage for reality as we know it. We're traveling back to the first sliver of a second after the Big Bang, to an era known as the Inflationary Epoch. This was not a slow, steady expansion. Imagine the universe smaller than a single proton, suddenly and exponentially exploding in size, doubling and redoubling its scale in fractions of a second so tiny they barely have names. During this incredible burst of growth, the universe expanded faster than the speed of light itself. Now, that might sound like it breaks the ultimate cosmic speed limit, but there's a fascinating loophole here. The rule that nothing can travel through space faster than light doesn't apply to the expansion of space itself. Space can stretch at any rate it likes, and during inflation, it did just that, inflating like a balloon being blown up at an unimaginable rate. This hyper-expansion did something extraordinary to time. In our calm, modern universe, time provides a steady beat, a reliable rhythm against which change can be measured. But back then, the frantic stretching of spacetime itself would have made the flow of time utterly chaotic and non-intuitive. The very arrow of time, the concept that points from the ordered past to the disordered future, might not have been firmly set. In the seething quantum foam of that infant universe, the distinctions we hold sacred between past, present, and future could have been blurred, even interchangeable. Time wasn't a smooth river flowing in one direction. It was more like a turbulent, boiling pot of water, with bubbles of causality forming and popping in a frenzied dance. This primordial state suggests that the linear, orderly progression of time we experience today isn't a fundamental rule, but a condition that emerged as the universe cooled and settled down, a pattern woven into the cosmic fabric only after this incredible inflationary period. And within that chaos, something beautiful and crucial happened. The universe wasn't perfectly smooth. At the tiniest quantum scales, there were constant fluctuations, virtual particles flickering in and out of existence as they always do. Under normal circumstances, these fluctuations are microscopic and short-lived, but inflation acted like a cosmic amplifier, stretching these tiny quantum ripples across the entire sky. In an instant, microscopic randomness was blown up to astronomical proportions. Those minuscule imperfections became the seeds for everything to come, the gravitational blueprints for the first galaxies, stars, and eventually us. This means the grand cosmic web we see today, with its vast filaments of galaxies and immense voids, has its origin in quantum uncertainty magnified by inflationary expansion. The universe wove its own large-scale structure from the smallest possible threads. The implications of this don't stop at the edge of our observable universe. Leading cosmologists like Alan Guth, who first proposed the theory of inflation, suggest this process might not be a one-time event. The mechanism that drove inflation could be eternal, constantly creating new, bubble universes in an ever-growing multiverse. Each of these bubbles could have its own unique set of physical laws and constants. Some might have stronger gravity or no light, or dimensions we can't even conceive of. And crucially, each of these universes could have its own arrow of time, or perhaps no clear direction of time at all. In this breathtaking view, our entire cosmic history, with its 13.8 billion-year timeline, is just one thread in an infinitely larger and more complex tapestry. Our experience of time flowing from a definite beginning toward an uncertain future is not the universal rule, but simply a local bylaw in our particular bubble. This transforms time from a passive backdrop into an active, dynamic participant in the story of the cosmos. The inflationary epoch wasn't just something that happened in time. It was an event that helped define what time itself would become for us. It set the initial conditions that allowed galaxies to form, stars to ignite, and planets to coalesce. It created the vast, dark, and expanding stage upon which the drama of cosmic evolution could unfold. Without this period of rapid weaving, the universe might have remained a smooth, featureless soup, devoid of structure and thus devoid of the complexity necessary for life. Reflecting on this origin story allows us to see that time is not a mere parameter we measure with clocks, but a deeply woven property of reality, one that emerged from a primordial state of boundless potential and continues to shape the destiny of everything we see. Yet if the inflationary epoch showed us the universe stretching its canvas on a monumental scale, our next journey takes us in the exact opposite direction, into the deepest, smallest, and most fundamental layer of reality itself. We are shrinking down past atoms, past protons, past even the fundamental particles, to a realm so tiny it defies visualization. This is the Planck scale, a domain where the very concepts of here and now begin to dissolve into a seething, chaotic frenzy known as quantum foam. To call it a place feels almost insufficient. It is more like the raw, unprocessed code of the universe, the fundamental substrate from which everything, including time itself, is woven. Imagine trying to look at the surface of a perfectly calm pond with a microscope of infinite power. At our everyday scale, the water appears smooth and glassy. But as you zoom in, you'd see molecules jostling. Zoom in further, and you'd find a world of incredible turbulence and constant motion. Now, take that idea and apply it to the fabric of spacetime itself. According to the principles of quantum mechanics and general relativity, at the unimaginably small scale of the Planck length, about a millionth of a billionth of a billionth of a billionth of a centimeter, spacetime cannot maintain its smooth, elegant curvature. Instead, it is theorized to erupt into a chaotic, frothing storm. This isn't just empty space, it is a foam, a constantly bubbling sea of pure potentiality where tiny wormholes might spontaneously form and pinch off, where geometry fluctuates wildly between different configurations. In this realm, the idea of a void is an illusion. The vacuum of space is alive with violent, spontaneous activity. This is where the ghostly dance of virtual particles becomes the main event. Constantly, pairs of particles and antiparticles flicker into existence, borrowing energy from the universe for an impossibly brief moment before annihilating each other and paying back the debt. But in the quantum foam, this process isn't just happening, it is the process. The foam itself is this endless creation and destruction, a probabilistic storm where the very notions of something and nothing lose their meaning. And it is within this storm that our most fundamental understanding of time faces its greatest challenge. We perceive time as a smooth, continuous flow, a river moving in one direction. But the quantum foam suggests this is a grand illusion, a smoothing over of a much more jarring and granular truth. At this foundational level, time might not flow at all. Instead, it might advance in the tiniest possible increments, like the individual frames of a movie. Each frame is a Planck time 10 to the power of negative 43 seconds, and the universe is constantly flickering from one state to the next. Our conscious experience of a continuous present is simply our brain stitching these discrete moments together into a coherent narrative. The brilliant physicist John Wheeler, who coined the evocative term quantum foam, envisioned this as the ultimate foundation of reality. He suggested that the large-scale, smooth spacetime we experience is an average, a statistical smoothing of this unimaginably turbulent underlying sea, much like the smooth appearance of a beach from a distance, which up close is revealed to be made of countless individual grains of sand. This has a profound implication for causality, the principle that cause must always precede effect. In the foam, the extreme fluctuations could create situations where the distinction between cause and effect becomes blurred. Microscopic loops might form where an event could influence its own past, creating a kind of self-contained causal knot. While these effects would be vanishingly small and average out at our scale, their existence would mean that at the most fundamental level, the universe does not strictly obey the linear causality we hold dear. The arrow of time, it seems, is not an inherent property of the cosmos but an emergent one, a pattern that only becomes clear and consistent when you step back from the frenetic weave of the foam and look at the larger tapestry. This radical idea finds a home in modern theories like loop quantum gravity, which directly proposes that space and time are not continuous but are composed of tiny, discrete, indivisible loops, a literal fabric woven from finite threads. In this view, time doesn't exist as a background parameter. It emerges from the relationships and interactions between these fundamental units of space. Think of it like the temperature of a gas. A single air molecule doesn't have a temperature. Temperature is a property that emerges from the collective motion of trillions of molecules. Similarly, in loop quantum gravity, the smooth flow of time is a property that emerges from the complex interactions of a vast network of spacetime grains. This transforms time from a fundamental stage into a collective phenomenon, a story the universe tells itself through its interactions. Grasping the nature of quantum foam is not just an academic exercise. It represents the final frontier in our quest for a unified theory of physics. It is the violent intersection where the deterministic, geometric world of Einstein's general relativity collides head-on with the probabilistic, uncertain world of quantum mechanics. Understanding how spacetime behaves here is the key to unlocking a theory of quantum gravity, a single framework that can describe the universe from the largest galaxy cluster to the smallest vibrating string. It forces us to confront the possibility that time, the most familiar and intimate dimension of our lives, is ultimately a woven illusion, a beautiful and stable pattern emerging from a hidden sea of timeless, chaotic potential. Leaving behind the frenetic quantum foam, we now travel to an object that is, in its own way, just as extreme, the heart of a neutron star. Picture the aftermath of a supernova, one of the most violent explosions in the universe. When a massive star dies, it can leave behind not a quiet ember, but a cosmic diamond of unimaginable density. This is a neutron star. To grasp its nature, imagine taking our entire sun, a sphere over 860,000 miles across, and crushing it down into a city-sized ball no wider than Manhattan. The forces at work here are so immense that they fundamentally rewrite the rules of matter itself. Electrons are forced into atomic nuclei, merging with protons to become neutrons. The entire star becomes, in essence, a single, gargantuan atomic nucleus, a perfect, seamless ocean of nuclear material. And at the very core of this incredible object, the conditions become so bizarre that they begin to warp the fabric of time in ways we can barely comprehend. The gravitational pull on the surface of a neutron star is already mind-boggling, about 200 billion times stronger than Earth's. But as we venture inward toward the center, that gravity intensifies even further. According to Einstein's theory, gravity doesn't just pull on objects, it pulls on time itself. The stronger the gravity, the slower time flows. This means that if you could place two identical clocks, one at the center of the neutron star and another on its surface, they would tick at radically different rates. The clock at the center would fall behind, second by second, compared to its counterpart on the surface. From the perspective of someone far away in space, watching this unfold, time at the star's heart would appear to be dragging, flowing through molasses compared to the time everywhere else. But here's the truly fascinating part. This isn't a uniform effect. The change in the flow of time isn't just between the center and the surface, it's a gradient. Time is woven into concentric shells like the layers of an onion, each shell experiencing a slightly different rate of temporal passage based on its depth within the gravitational well. Over the mere miles between the surface and the core, time could be stretched by a significant factor. This creates an environment where the very concept of now becomes fragmented and local. Two events that appear simultaneous to an outside observer might not be simultaneous for someone or something existing at different depths within the star. Causality itself, the unbreakable rule that cause must come before effect, would have to navigate this complex, layered temporal landscape. It's a stark demonstration that time is not a universal metronome ticking away in the background of the cosmos. It is a dynamic, malleable dimension that is intimately woven into the distribution of matter and energy. The neutron star acts as a natural laboratory, demonstrating these relativistic effects on a dramatic scale, showing us that time and substance are two sides of the same cosmic coin. But the story of time within a neutron star doesn't end with gravity alone. These objects are often spinning at incredible speeds, some rotating hundreds of times per second. This rapid rotation introduces another relativistic effect known as frame dragging, where the spinning mass literally drags the fabric of spacetime around with it. This creates a kind of vortex in time and space, further complicating the already layered temporal structure. Additionally, some neutron stars evolve into magnetars, possessing magnetic fields so powerful they could strip the information from a credit card from 100,000 miles away. These titanic magnetic fields are thought to be capable of twisting the very crust of the star, causing starquakes that release immense bursts of energy. In such an environment, the interplay between crushing gravity, dizzying rotation, and unimaginable magnetism could create localized frames of reference where time doesn't just slow down, but might exhibit more complex, non-linear behavior. While we cannot peer directly into the heart of a neutron star by studying their pulses and vibrations, astrophysicists can infer the conditions within, using them as cosmic testbeds to probe the limits of physics and better understand how matter, in its most extreme forms, tells time itself how to behave. But the universe's catalog of extreme objects isn't limited to the static, all-consuming darkness we often imagine. Nature prefers to spin, and when a dying star with ample angular momentum collapses, it doesn't form a simple black hole. It creates a cosmic whirlpool of unimaginable ferocity. This is a rotating black hole, or a Kerr black hole, and its environs contain one of the most dynamically twisted regions of spacetime ever conceived, the ergosphere. If you thought the event horizon was strange, prepare to enter a zone where the very concepts of standing still and moving forward are ripped away from you, replaced by a mandatory, dizzying dance dictated by the black hole's relentless spin. Picture this region not as a sphere, but as a flattened oblate spheroid, a kind of cosmic halo that surrounds the event horizon itself, touching it at the poles but bulging out significantly around the equator. This is the ergosphere. Cross into this territory, and you encounter a phenomenon so counterintuitive it feels like a violation of physics itself, the frame-dragging effect. Predicted by Austrian physicists Joseph Lenz and Hans Thöring decades before Kerr found the precise solution, this effect states that a massive rotating object doesn't just create a gravitational well, it also creates a gravitational whirlpool, dragging the very fabric of spacetime around with it as it turns. Near Earth, this effect is infinitesimally small, though it has been meticulously measured by precise satellites. But at the edge of a spinning black hole, frame dragging isn't a subtle curiosity, it is the absolute law of the land. Within the ergosphere, spacetime itself is being pulled around in a circle at a significant fraction of the speed of light. The consequence is both simple and utterly bizarre. It becomes impossible to stand still. No matter how powerful your rockets, you cannot remain stationary relative to the distant stars. You are caught in a cosmic current, forced to move in the direction of the black hole's rotation. You retain some freedom. You can move with the current or fight it to move slightly against the flow, but you cannot stop paddling. To do so would require moving faster than the speed of light backwards, which the universe forbids. This relentless drag has a profound implication for the nature of time within this zone. In our everyday experience, time and space feel like independent stages. We move through space at will, while time marches on regardless. But in the ergosphere, this independence shatters. Time becomes inextricably coupled to motion through space. The direction of your movement through space directly influences your personal experience of time's flow. This creates a woven temporal landscape where future isn't a single direction ahead of you, but is instead twisted around the black hole's axis of rotation. Your future is quite literally being dragged in a circle. This is the ultimate expression of Einstein's relativity, where time is not a universal constant but a flexible dimension woven into the geometric fabric of the universe, and that fabric is being spun like a potter's wheel. This bizarre environment isn't just a theoretical curiosity, It offers a potential goldmine of energy through a brilliant thought experiment known as the Penrose process. Imagine a sophisticated advanced civilization needing a power source. They could send a mission into the ergosphere of a rotating black hole. Once inside, they could launch a projectile or split an object into two parts. If timed precisely, one fragment could be directed to fall into the black hole's event horizon, losing rotational energy and angular momentum, while the other fragment, with now more energy than it started with, escapes back out into the universe. This process effectively steals rotational energy from the black hole itself, slowly causing it to spin down. The energy doesn't come from nothing. It is extracted from the black hole's immense rotational inertia, a direct harnessing of the twisted spacetime in the ergosphere. It's a concept that transforms a black hole from a purely destructive end into a potential engine, a cosmic battery powered by the most extreme physics imaginable. The very existence of the ergosphere and phenomena like the Penrose process demonstrate that angular momentum is not just a property of objects in spacetime, but a fundamental sculptor of spacetime itself. It shows us that time is not a passive backdrop against which the universe plays out, but a dynamic and pliable entity that can be stirred, twisted, and even mined for energy by the motion of matter. The rotating black hole with its ergosphere stands as a powerful testament to the fact that the universe is not static. It is a place of constant dynamic motion, and that motion is woven directly into the ticking of every clock. While the spinning ergosphere of a black hole demonstrates how motion can twist the fabric of reality, our journey now takes us to a far more subtle, yet equally profound kind of cosmic imperfection. To find it, we must venture back to the universe's very first moments, to a time of unimaginable energy and transition. Picture the newborn cosmos cooling rapidly after the Big Bang, much like water freezing into ice. And just as ice forms with cracks and fissures as it freezes, the very fabric of spacetime may have crystallized with its own kind of flaws, cosmic strings. These are not strings in the everyday sense, but hypothetical, incredibly thin, and unimaginably dense filaments of pure energy, thinner than a proton but stretching across the entire observable universe. They are thought to be one-dimensional defects, cracks in the geometric foundation of reality itself, left over from when the fundamental forces of nature split apart from their initial unity. The sheer density of a cosmic string is staggering. A single inch of one might contain more mass than a mountain range, warping the spacetime around it into a sharp, conical shape. Imagine spacetime as a flat, stretched rubber sheet. Placing a heavy ball on it would create a smooth, curved depression. This is how planets and stars warp space. Now imagine taking a razor blade and making an incredibly precise, perfectly straight cut in that sheet, then sewing it back together so that a tiny wedge of material is missing. The sheet would now have a sharp crease along that line. This is the kind of geometry a cosmic string creates. It doesn't make a smooth gravitational well. It creates a deficit angle, a permanent crease in the universe. Any light or matter passing near this crease would find its path subtly altered, not by being pulled inward, but by effectively having to travel around a hidden corner in geometry. This bizarre warping is the first clue to how cosmic strings could manipulate time. The most extraordinary possibility arises when these strings are not static, but moving. If two cosmic strings were to pass by each other at a significant fraction of the speed of light, the complex interplay of their intersecting spacetime creases could, in theory, create a closed time-like curve, a path through the universe that loops back onto itself. An object following this path would not journey to a new location in space, but to a moment in its own past. This configuration essentially acts as a gravitational time machine, using the geometry of spacetime itself to weave time into a loop. The mathematics from general relativity allows for this possibility, but it comes with immense practical challenges. The energies required are far beyond anything we can conceive of creating, and the stability of such a system is highly questionable. Furthermore, as with wormholes, the potential for paradoxes might mean that quantum effects would always conspire to prevent such a loop from being used, perhaps through a buildup of intense radiation that destroys the configuration the moment it becomes a time machine. It remains a breathtaking theoretical playground, a testament to the fact that the universe's rulebook might allow for things that seem, to our human intuition, utterly impossible. Beyond the tantalizing prospect of time loops, cosmic strings are a window into a broader class of phenomena known as topological defects. These are stable, persistent structures that can form in any system undergoing a phase transition, like the bubbles that form when water boils or the magnetic domains in a cooling piece of iron. In the early universe, as the underlying quantum fields that govern reality cooled and settled into their current state, they may not have done so perfectly uniformly. Different regions could have chosen different, equally valid, lowest energy states. Where these different regions met, their boundaries could have become trapped as stable defects. Cosmic strings are just one type. Theorists also speculate about two-dimensional sheets called domain walls, or point-like defects called magnetic monopoles. Each of these represents a kind of cosmic fossil, a frozen-in remnant of a more symmetric, hotter past. Their existence would be a direct, observable signature of the grand unified theories that physicists are striving to prove, offering tangible evidence for the processes that shape the laws of physics themselves. The search for cosmic strings continues, though they have so far eluded detection. Astronomers look for their telltale signatures, such as double images of a single galaxy created by gravitational lensing from the string's sharp crease, or unique ripples in the cosmic microwave background radiation. While no definitive evidence has been found, the very fact that we can conceive of such objects expands our understanding of the cosmos. They teach us that the universe might not be perfectly smooth and featureless in its geometry. It could be textured, with wrinkles and scars and defects woven into its very fabric from the moment of its birth. These imperfections are not flaws in the sense of errors. They are a natural and predicted consequence of the universe's dramatic evolution. In contemplating cosmic strings, we are forced to consider that time might not be a pristine, independent river, but a dimension that can be pinched, creased, and potentially even looped by the topological architecture of spacetime itself, revealing a cosmos that is far more intricate and geometrically rich than it appears. But if cosmic strings represent threads of incredible density woven through our universe, our next destination forces us to expand our view to a scale so vast it redefines the very meaning of everything. We must venture beyond the confines of our single cosmos to the frothing, bubbling frontier of the multiverse itself. Picture not one universe, but an infinite, ever-expanding sea of them, each a separate bubble of spacetime nucleating and inflating within a grand, meta-cosmic background. This is the theory of eternal inflation, and it suggests our entire cosmic history is just one bubble among countless others in a foam of universes. And at the edges of these bubbles, where one expanding realm of reality brushes up against another, we find a boundary where the nature of time itself is up for grabs, a place where the rules we take for granted are merely local ordinances. This idea emerges from the same inflationary theory that describes our universe's explosive beginning. But instead of inflation stopping everywhere at once, the proposal is that it only stops in localized patches. In these patches, a stable universe like ours forms and cools. But outside these bubbles, in the wider meta-universe, the high-energy inflationary state continues unabated, constantly giving birth to new bubble universes. It's a never-ending process, an eternal chain reaction of cosmic creation. Each of these bubbles could have its own unique set of physical constants. The strength of gravity, the mass of an electron, the number of spatial dimensions, these fundamental parameters could be different in every single one, determined by the random chance of how that particular bubble formed. In some, the forces might be too weak for atoms to ever form. In others, stars might burn out in an instant. Our universe, with its seemingly fine-tuned constants that allow for galaxies, planets, and life, would be just one lucky roll of the dice in a cosmic casino of infinite possibilities. Now, imagine the boundary of one of these bubbles. It's not a physical wall you could touch. It's a domain wall, a region of incredibly high energy where the inflating false vacuum outside meets the stable, low-energy vacuum inside our universe. This frontier is a place of immense tension and violent transition. As two bubbles expand, their boundaries will eventually collide. When they do, the energy released would be cataclysmic, sending ripples through the very fabric of spacetime within both bubbles. These ripples would propagate as gravitational waves and could potentially leave a faint, circular imprint on the oldest light we can see, the cosmic microwave background. Astronomers are actively searching the CMB for these telltale patterns, hunting for the cosmic bruises that would be the first hard evidence that our universe is not alone, that we indeed have neighbors in the multiverse. It is at these chaotic boundaries where the nature of time becomes truly unshackled. Within our bubble, we experience a strong, consistent arrow of time, pointing from the low-entropy Big Bang toward a high-entropy future. This directionality is tied to the specific initial conditions and laws of physics within our universe. But in another bubble, with different laws and a different initial state, the arrow of time could point in a completely different direction, or there might be multiple arrows of time, or perhaps no clear direction at all. At the moment of a bubble collision, as two vastly different spacetimes with potentially different temporal architectures slam together, the very concept of causality could be thrown into disarray. An effect in one universe could, for a fleeting moment at the boundary, become the cause for an event in the other, weaving a thread of connection between two timelines that were previously independent. For observers safely inside their own bubbles, time would appear to flow normally, its local rules undisturbed. But for a hypothetical being able to perceive the multiverse as a whole, time would be a fractured, multifaceted tapestry, with each thread representing a universe with its own unique rhythm and direction of temporal flow. This breathtaking vision, championed by cosmologists like Alexander Vilenkin, fundamentally demotes time from a universal constant to a local variable. It suggests that the flow of time is not an inherent property of existence but an emergent feature that depends entirely on the specific physical environment you find yourself in. Our experience of a linear, one-way progression from past to future is not the cosmic standard. It is simply the way time works in our particular neighborhood. This idea pushes the limits of not only physics but of philosophy, forcing us to confront the possibility that the memories we hold dear and the future we anticipate are not absolute truths written into the universe, but are instead intimate features of our own local cosmic story. The boundary of a bubble universe is thus the ultimate frontier, a place where the tapestry of time is not just woven, but where entirely new and different tapestries are being stitched together into a grand, multiversal quilt of reality. But if the crushing finality of a black hole singularity represents one extreme of cosmic destiny, its theoretical opposite offers a vision of pure, explosive creation. Imagine a celestial event so antithetical to a black hole that it defies every instinct we have about how the universe operates. We are now venturing into the realm of the white hole, a place where gravity's relentless pull is replaced by an unstoppable push, where the universe doesn't consume but instead violently expels. While a black hole is a cosmic drain from which nothing can escape, a white hole would be a cosmic fountain from which nothing can enter. It is a region of spacetime where matter and energy erupt outward in a dazzling, furious burst, a permanent and impassable explosion frozen in time. This isn't just a different kind of object, it's a mirror image, a negative print of a black hole's reality, and it forces us to confront the astonishing possibility that the arrow of time itself might not be a universal constant, but a local condition that can, under the right circumstances, actually run in reverse. The mathematics that give rise to this incredible idea are not newfangled speculation. They are embedded within the same equations of general relativity that predict black holes. When Karl Schwarzschild first found a solution to Einstein's field equations describing a non-rotating, point-like mass, the result actually described two distinct regions, the black hole we are familiar with and its theoretical twin, the white hole. In the complex geometry of this solution, a white hole represents a part of the universe that is eternally in the past of the black hole. It is a one-way street in the opposite direction. While you can fall into a black hole, you can only ever exit a white hole. You could no more enter a white hole than you could travel back in time and undrop a glass of water, catching all the scattered pieces and reassembling them perfectly on the table. The very laws of physics as described by these equations would prevent it. This makes white holes incredibly fragile concepts. Any speck of dust, any single photon of light attempting to approach it would violate its fundamental nature, and most physicists believe this is why we have never observed one. They are mathematically possible, but physically unstable in our universe, likely collapsing instantly into something else the moment they try to form. This instability, however, hasn't stopped theorists from exploring the profound implications of white holes, particularly when it comes to the nature of time. If we could observe a white hole in action, its behavior would appear to us as a perfect video of a black hole being played in reverse. Instead of a star collapsing silently into an infinitely dense point, we would see a singularity violently exploding, spewing out all the matter and energy it had ever contained, rebuilding stars and planets from a point of infinite energy. From our perspective, this would look like effects wildly preceding their causes. We would see the reassembled debris of a galaxy before witnessing the explosive event that created it. This inverted causality presents a direct challenge to our most fundamental experience of reality, suggesting that the forward flow of time we hold so dear might not be an absolute rule of the cosmos, but merely the dominant direction in our particular region of spacetime. Inside a white hole, time would be woven into a tapestry where the threads of cause and effect are not just tangled, but are running backwards through the loom. This bizarre concept finds a surprising and modern application in one of the most active fields of theoretical physics, resolving the black hole information paradox. Some quantum gravity approaches, particularly in loop quantum cosmology, propose that the terrifying singularity at the heart of a black hole might not be the ultimate end. Instead of collapsing to an infinite density, the immense quantum pressure at the core could cause the collapsing matter to bounce, much like a ball compressed to its limit will spring back. In this scenario, what we perceive as a black hole, an object that only absorbs, could, after an unimaginably long period of time, undergo a quantum phase transition and become a white hole, beginning to radiate out all the information it once swallowed. This would provide an elegant solution to the paradox, preserving the information of everything that fell in by eventually releasing it back into the universe. In this view, the tiny, long-evaporated black holes theorized to have formed in the early universe might now be reaching the end of their lives, popping off like cosmic firecrackers as microscopic white holes, pouring their stored information back into the cosmos in a burst of high-energy radiation. Contemplating white holes, therefore, is far more than an exercise in mathematical fantasy. It is a powerful tool that expands our view of time's flexibility and the universe's potential symmetry. It challenges the finality of black holes and suggests that even the most destructive processes in the cosmos might be part of a grand, cyclical dance of collapse and rebirth. While we may never directly observe a white hole in the wild, the mere fact that our best theory of gravity allows for such a concept tells us that the universe is capable of geometries and histories far stranger than our everyday experience would ever suggest. The white hole stands as a testament to the idea that the arrow of time might not be a fundamental law written in stone, but an emergent property, a local curvature in the grand tapestry of spacetime that somewhere else could be pointing in a completely different direction. Yet for all the theoretical freedom that general relativity offers, painting a cosmos rich with temporal loops and cosmic shortcuts, our everyday reality remains stubbornly linear. We remember the past, we anticipate the future, and we never encounter a younger version of ourselves walking down the street. This profound disconnect between what the equations allow and what we actually experience led one of the 20th century's greatest minds to propose a kind of cosmic law enforcement. Stephen Hawking, with his characteristic wit, once famously declared, "I have experimental evidence that time travel is not possible. I didn't get invited to my own time traveler's party." Behind that joke lay a deep physical intuition that became known as the chronology protection conjecture, a proposal that the universe has a built-in safety mechanism, a principle that actively works to prevent paradoxes and preserve the orderly flow of cause and effect that we all rely on. This conjecture isn't about finding a specific location on a star chart. You can't point a telescope at the chronology protection region. Instead, it represents a conditional boundary, a set of physical circumstances that automatically trigger whenever the fabric of spacetime is manipulated in a way that threatens to create a closed time-like curve, a path that loops back into its own past. Imagine an engineer in the far future attempting to activate a wormhole time machine. According to Hawking's idea, the very moment the machine is powered up to create a path to yesterday, a cascade of quantum effects would be unleashed. Virtual particles, those fleeting fluctuations of the quantum vacuum, would begin to circulate through the nascent time loop. With each pass, their energy would amplify, building up exponentially in a runaway feedback loop that would quickly become infinite. This unimaginable surge of energy would inevitably destroy the wormhole or whatever other structure was being used, shutting down the time travel route before a single photon could ever complete a journey to the past. The universe, in this view, acts like a sophisticated immune system, identifying temporal paradoxes as a threat to logical consistency and deploying an overwhelming quantum response to neutralize the danger before it can ever manifest. This proposed mechanism highlights a fascinating and fundamental tension at the heart of modern physics. On one hand, we have Einstein's general relativity, a theory of breathtaking beauty and geometric elegance that seems to permit all sorts of exotic spacetime geometries, including those that allow for time travel. Its equations are time-symmetric and don't inherently care about preserving a one-way arrow of time. On the other hand, we have quantum mechanics, which is deeply concerned with probabilities, observations, and the unidirectional increase of entropy, a concept that gives us our psychological and thermodynamic arrow of time. The chronology protection conjecture sits right at the violent intersection of these two titanic theories. It suggests that while relativity might provide the blueprints for a time machine, quantum physics provides the building inspector who immediately condemns the structure as unsafe. The universe seems to value causal order above all else, weaving time in such a way that on the large human scale, it appears smooth, linear, and paradox-free. Even if at the ultra-tiny Planck scale, there might be a chaotic froth where such distinctions blur. Ultimately, Hawking's profound idea offers a comforting, if somewhat limiting, resolution. It tells us that the reason we don't see time travelers might not be because the engineering challenge is too great, but because the laws of physics fundamentally forbid it. The cosmic censorship he proposes protects not just the timeline from paradox, but it also protects the very concept of reality as a coherent, single history. It ensures that our memories are reliable records of actual events and that our actions have predictable consequences. In a universe without chronology protection, the foundation of science, history, and even personal identity would crumble into a chaotic jumble of contradictory events. So, while we might wistfully dream of visiting ancient Rome or witnessing the future, Hawking's conjecture paints a picture of a universe that is rational and self-consistent at its core, employing the most advanced laws of quantum physics to act as the ultimate guardian of its own timeline, meticulously weaving causality into the very fabric of existence to keep the story of reality moving forward in a way that always and only makes sense. Leaving behind the mind-bending physics of cosmic censorship, we now turn our gaze outward to the very largest scale we can possibly perceive. We are looking toward the ultimate horizon, the final frontier of observation itself, the edge of the Hubble volume. This is not a physical boundary like a wall or a membrane. It is the limit of our knowledge, the farthest reach of light since the dawn of time. To stand at this edge is to stare back 13.8 billion years into the past, to witness the universe in its fiery infancy. But this horizon is not static. It is receding from us at an ever-increasing rate, and the physics governing this expansion weaves time into a fabric of such profound relativity that it challenges the very notion of a shared cosmic present. To understand this, we must first grasp what the Hubble volume truly represents. Imagine a sphere centered on Earth, with a radius defined by the distance light has had time to travel since the Big Bang. Everything within that sphere is our observable universe. Every star, every galaxy, every photon that has ever reached our telescopes lies inside it. But here's the crucial part. Due to the metric expansion of space, the fact that the very fabric of the cosmos is stretching, the most distant galaxies are being carried away from us at velocities that increase with distance. At the very edge of our observable sphere, those recession velocities approach the speed of light itself. This creates a cosmic horizon, a point beyond which we cannot see, not because our telescopes aren't powerful enough, but because the light from those regions can never reach us. The space between us and them is expanding faster than light can traverse it. This is where time itself becomes stretched to its absolute limit. Due to this incredible velocity, the relativistic effects of time dilation become extreme. From our perspective here on Earth, a clock situated in a galaxy at the very edge of the Hubble volume would appear to have almost completely stopped. Its ticks would be stretched out over millennia, its processes frozen in an eternal moment from the early universe. For any beings in that distant galaxy, their local time would feel perfectly normal. They would experience the steady progression of seconds, minutes, and years. But their now and our now are not the same. We are seeing them as they were billions of years ago, and from their viewpoint, if they could see us at all, they would be looking back at a young, hot Earth that had yet to form its first single-celled organism. There is no universal clock ticking away in the background. Instead, time is woven directly into the expanding fabric of the cosmos. with each observer at each point in space experiencing their own personal, relative flow of time, all dictated by their position within the grand, stretching tapestry of spacetime. This incredible variation is governed by a key number in cosmology known as the scale factor. Think of the universe as a loaf of raisin bread rising in the oven. The raisins represent galaxies and the dough represents space. As the bread rises, every raisin moves away from every other raisin, not because they are traveling through the dough, but because the dough itself is expanding. The scale factor simply tells us how much the dough has stretched between any 2 points in time. The rate of this stretching is what determines the Hubble constant, the value that tells us how fast a galaxy is receding from us based on its distance. This scale factor doesn't just measure distance, it directly influences the passage of time across cosmic scales. As the universe expands, it literally stretches the wavelength of light traveling through it, shifting it toward the red end of the spectrum. This cosmological redshift is not just a Doppler shift from motion through space. It is a direct measure of how much the universe has expanded during the light's journey, and therefore, how much time has been stretched and distorted along the way. Contemplating the Hubble volume edge is a profoundly humbling experience. It defines the ultimate limit of our empirical knowledge. We can theorize about what lies beyond, but we can never observe it. That region is causally disconnected from us forever. This horizon is also dynamic. As time passes, the expansion of space means that galaxies that are visible to us today will eventually be carried beyond this horizon, their light too redshifted and too faint to ever detect again. The observable universe, in a sense, is slowly fading away, isolating our galaxy in a vast, ever-growing sea of darkness. This reveals the most intimate link between time and the large-scale structure of the universe. Time is not separate from space. It is a thread inextricably woven into it. The expansion of the cosmos doesn't just happen in time. It actively dictates how time flows for different observers across the vast distances, creating a reality where there is no single present moment, but a mosaic of nows that vary depending on where you are in the expanding continuum. But to truly grasp the power of this quantum underworld, let's journey from the cosmic scale down to a laboratory bench, where one of the most elegant experiments in all of physics makes these invisible forces tangible. We now arrive at our 13th destination, a place not of astronomical scale, but of exquisite microscopic precision, the Casimir Effect vacuum. Forget distant galaxies or black holes. This phenomenon unfolds in a small, controlled chamber between two impeccably smooth metal plates placed mere nanometers apart. It's here, in this seemingly sterile and empty space, that we find one of the most direct and compelling pieces of evidence that the void is not empty at all, but is instead a seething, dynamic arena where the very threads of spacetime are constantly being woven and rewoven. The setup is deceptively simple. Imagine two perfectly flat, uncharged mirrors placed facing each other in a complete vacuum, a space we have pumped clean of every atom, every molecule, every known particle. Classical physics would tell us that absolutely nothing should happen between them. There is no gravity, no electromagnetism, no force to act upon them. They should remain perfectly, inertly still. Yet, when scientists perform this experiment, an utterly mysterious thing occurs. The two plates are irresistibly pulled together by a faint but measurable force. This is the Casimir Effect, named after the Dutch physicist Hendrik Casimir, who first predicted it in 1948. For decades, it was a curious theoretical prediction, but it has since been measured with astounding accuracy, confirming that even in a perfect vacuum, there is a ghostly presence at work. The explanation for this bizarre attraction lies in the bizarre rules of quantum mechanics and the nature of the vacuum itself. we traditionally think of a vacuum as true nothingness, a void. But quantum theory paints a radically different picture. What we call empty space is actually a turbulent sea of fleeting energy. Constantly, everywhere, pairs of virtual particles, and their antiparticles spontaneously blink into existence, borrowing energy from the universe for an infinitesimally short time before colliding and annihilating each other, paying back the energy debt. This isn't just a mathematical quirk, it's a fundamental property of reality, and these virtual particles exert real physical pressure. Now, picture our two metal plates placed extremely close together. Outside the plates, in the wider vacuum, virtual particles of all possible wavelengths can pop into being. But in the narrow gap between the plates, only certain wavelengths of light, or photons, can exist specifically, those whose wavelengths fit perfectly as fractions of the gap distance. It's like the way only certain musical notes can resonate inside an organ pipe. This restriction means that there are fewer possible virtual particle fluctuations happening in the gap between the plates than there are in the open space outside them. With more virtual particles pushing on the outer surfaces of the plates than on the inner surfaces, the net result is an inward pressure that forces the plates together. The emptiness itself is pushing them into an embrace. This incredible effect is a direct demonstration that what we perceive as empty space is actually brimming with energy, a roiling substrate now known as the quantum vacuum or zero-point energy. The Casimir effect proves that this vacuum energy is not just a theoretical concept. It has tangible mechanical consequences, warping the geometry of spacetime on a tiny scale to create a force where none should exist. It shows us that spacetime is not a passive stage but an active participant, its properties shaped and modified by the underlying quantum frenzy. In the gap between those plates, the very fabric of reality is different. The vacuum energy density is altered, and with it, the local properties of spacetime itself. This leads to a profound and thrilling possibility. If we can manipulate the quantum vacuum to create forces, could we also manipulate it to influence time? Some theoretical work suggests that extreme configurations involving the Casimir effect, perhaps using specially designed materials or shapes, could create regions where the energy density of the vacuum becomes negative. This exotic quantum state is precisely the kind of exotic matter that theoretical models like those of Kip Thorne indicate would be necessary to stabilize a traversable wormhole, a shortcut through spacetime. While we are fantastically far from engineering anything of the sort, the principle is established in our physical laws. By manipulating the quantum vacuum, we are, in essence, tweaking the very loom on which spacetime is woven. The Casimir effect is a tiny, laboratory-scale hint of the kind of spacetime engineering that might occur naturally near the event horizons of black holes or in the primordial universe, demonstrating that the seeds of cosmic time weaving are present right here in experiments on Earth. This beautiful experiment serves as a crucial bridge between the two great pillars of modern physics, the quantum world and the relativistic world. It takes a quantum phenomenon, virtual particle fluctuations, and produces a result, a force that can be measured with classical instruments. It shows that quantum effects are not confined to the atomic scale. They can cascade up to influence the macroscopic world, warping spacetime in a way that Einstein would recognize. The Casimir effect is a humble, human-scale window into the profound truth that non-linear time and woven spacetime are not just theoretical fantasies for astronomers. They are principles of reality that we can interrogate, measure, and begin to understand right here in the lab, reminding us that the universe's greatest mysteries are often hidden in the quietest of places. While the quantum Casimir effect reveals the hidden energy of the void on the smallest scales, we now journey to the opposite extreme, to the very largest structures that gravity has ever built. Imagine not a single star or even a single galaxy, but a metropolis of galaxies, a sprawling gravitational city where thousands of galaxies swarm together, bound by their mutual attraction and the immense, invisible grip of dark matter. This is a galaxy cluster, the largest gravitationally bound structure in the entire universe, and at its heart lies a core of such incredible density and power that it doesn't just bend light, it bends time itself, weaving it into a unique, slowed-down rhythm that echoes throughout the cosmic web. To truly appreciate the scale, consider our own Milky Way. It's a vast island of hundreds of billions of stars. Now, picture 1,000 more galaxies just like it, all drawn together into a single, immense structure that can span millions of light years. The core of such a cluster is a place of extremes. It's filled with a superheated plasma, gas so incredibly hot that it shines not in visible light, but in powerful X-rays, revealing a thermal bath of over 10 million degrees. But even more significant than this visible inferno is the dark matter. This mysterious, invisible substance, which does not emit or absorb light, makes up the vast majority of the cluster's mass. It is the dark matter that provides the deep gravitational well, the unseen scaffolding that holds the entire colossal structure together. It is in this core, where both luminous gas and dark matter are at their most dense, that the gravitational potential becomes so deep it begins to directly manipulate the fabric of spacetime. This manipulation has a direct and measurable consequence: time dilation. According to Einstein's general relativity, time runs slower in a stronger gravitational field. We see a tiny, practical version of this every day. The GPS satellites orbiting Earth have to account for the fact that their clocks tick very slightly faster than clocks on the ground due to the difference in gravity. Now amplify that effect by a factor of millions. In the deep gravitational well at the heart of a galaxy cluster, time itself is stretched and slowed. A clock placed there would tick measurably more slowly than a clock in the relative emptiness of intergalactic space. This isn't a theoretical abstraction. It's a real, physical effect that cosmologists can, in principle, infer by observing the light that escapes from these regions. The immense gravity redshifts the light, stretching its wavelength and effectively stealing energy from it, a process that is intrinsically linked to the slowing of time at the source. This creates a woven temporal environment where the flow of time is not a universal constant but a local variable, directly dictated by the amount of mass energy concentrated in one place. This profound distortion of spacetime doesn't just affect time, it also warps the paths of light itself, leading to one of astronomy's most powerful tools, gravitational lensing. The colossal mass of the cluster's core acts like a gigantic lens, bending and distorting the light from even more distant galaxies lying behind it. This lensing can create spectacular effects, multiple images of the same background galaxy, or smear them into long, faint arcs of light like cosmic smiles. But this lensing is more than just a pretty picture. It is a direct map of the gravitational field, and therefore a map of the woven space-time itself. By studying how the light is bent, astronomers can precisely weigh the cluster, mapping the distribution of both the hot gas we can see and, crucially, the dark matter we cannot. The distorted images are a signature of warped space and time, allowing us to literally see the invisible scaffolding of the cosmos. Studying these colossal cores is therefore about much more than cataloging giant structures. They serve as immense natural laboratories for testing Einstein's theory of gravity on a scale he could never have imagined. They allow us to probe the nature of dark matter, constraining its properties by observing how it clumps and shapes these gravitational wells. And they provide the most dramatic evidence that time is not a uniform backdrop. Across the universe, in the hearts of these great clusters, time flows at a different rate than it does in the voids between them. The cosmos is not ticking to a single master clock. Instead, it is a vast and varied tapestry of temporal experience, with each thread, each region of space keeping its own time, woven into the fabric of reality by the distribution of matter and energy within it. The core of a galaxy cluster stands as a monumental testament to this fact, a place where gravity's patient work over billions of years has created a gravitational cathedral where time itself is compelled to kneel and slow its perpetual march. Imagine a city-sized sphere of pure nuclear matter, spinning faster than a kitchen blender and possessing a magnetic field so powerful it could wipe every credit card on Earth from half the distance to the moon. This isn't a science fiction weapon. It's a magnetar, and its surface is one of the most violently dynamic environments in the entire cosmos. We've already seen how the immense gravity of a neutron star warps time, but a magnetar introduces a new, terrifyingly powerful actor to the stage: magnetism on a scale that literally bends the fabric of spacetime itself. Here, the forces that make a refrigerator magnet stick are amplified a trillion times, creating a realm where the universe's fundamental rules are not just bent, but twisted into entirely new shapes. The sheer intensity of this magnetism is almost impossible to comprehend. If a magnetar were located even as far away as our moon, its magnetic field would be strong enough to strip the electrons right off the atoms in your body, effectively disassembling you from 250,000 miles away. On its surface, this field doesn't just exist as an invisible force. It physically warps the star's incredibly dense crust, which is harder than diamond. The magnetic stresses are so immense that they periodically cause the crust to fracture and shift in catastrophic events known as starquakes. Picture an earthquake, but on an object with the density of an atomic nucleus, releasing more energy in a millisecond than our sun emits in 100,000 years. These bursts of energy, often observed as soft gamma-ray repeater flares, are among the most powerful explosions known in the universe since the Big Bang itself. This is where time itself gets caught in the crossfire between gravity and magnetism. We know from general relativity that any form of energy, not just mass, can warp spacetime. A magnetic field contains a tremendous amount of energy, and a magnetar's field is so concentrated and energetic that it contributes significantly to the curvature of spacetime around the star. This means the time dilation effects here are a complex cocktail, brewed from both the deep gravitational well of the neutron star and the additional contortions imposed by the magnetic field. A clock on the surface of a magnetar wouldn't just tick slowly due to gravity. Its rate could be further altered, in principle, by the magnetic field's own influence on the local spacetime geometry. Furthermore, the star's rapid rotation drags spacetime around with it, a phenomenon known as frame dragging, and the magnetic field could potentially influence this vortex, creating a layered, dynamic temporal environment where the flow of time is tugged in multiple directions at once. The most dramatic temporal effects might not be smooth and constant, but sudden and jerky, tied directly to the magnetar's violent tantrums. During a starquake, the instantaneous release of energy is so vast and concentrated that it could create a fleeting, localized distortion in spacetime, a tiny ripple in time itself. For an infinitesimally brief moment, the rules of causality could stutter. While these effects would be too small and fast to measure from Earth, they represent a fascinating possibility that time might not always be a smooth, flowing river. In the most extreme places, it could behave more like a stream encountering rocks, with moments of turbulence and sudden shifts in its current. This challenges the notion of time as a universally uniform parameter, suggesting instead that its passage can be punctuated by violent events that leave their mark on the temporal landscape. Studying magnetars, therefore, is not just about cataloging cosmic oddities. They are unparalleled natural laboratories for probing the intersection of the universe's fundamental forces under conditions we could never hope to recreate on Earth. They show us that the weaving of time is not the sole domain of gravity. Electromagnetism, the force behind light and chemistry, can also become a powerful loom on its own when taken to its absolute extreme. By observing the pulses of radiation from these spinning stellar corpses, astronomers can test the limits of quantum electrodynamics and general relativity simultaneously, searching for tiny deviations that might hint at new physics. Each flicker of light from a magnetar's surface carries encoded information about the brutal forces at work, telling a story of a reality where time is not a passive backdrop but an active, pliable dimension, constantly being kneaded and reshaped by the titanic clash between matter, gravity, and magnetism. But if the violent, dynamic surface of a magnetar represents one extreme of time's behavior, our next destination invites us to contemplate a phenomenon of profound stillness and ancient light, a whisper from the very dawn of everything. We are turning our attention to the oldest and most distant thing we can possibly perceive, not an object, but a pervasive, a gentle glow that fills the entire cosmos. This is the cosmic microwave background radiation, or CMB, and it is nothing less than the faded afterglow of the Big Bang itself, a fossilized snapshot of the universe when it was a mere 380,000 years old. To study this light is to open a window directly into the universe's infancy, and encoded within its subtle patterns are secrets that could rewrite our understanding of time's most fundamental nature. Imagine the universe in its earliest moments, a seething, opaque plasma, hotter than the core of any star, where light was constantly trapped, scattered by a dense fog of free electrons and protons. It was a world without stars, without galaxies, without clear sight. Then, in a pivotal moment, the expansion of the universe finally cooled things enough for electrons and protons to combine into neutral hydrogen atoms. In an instant, the cosmic fog lifted, the universe became transparent, and that first burst of liberated light began its journey across the cosmos. That light, stretched and cooled by 13.8 billion years of relentless expansion, is what we detect today as the CMB, a nearly uniform microwave static that comes from every direction in the sky, bathing the entire universe in a thermal echo of its own violent birth. This isn't just ancient light, it's a time capsule of unparalleled fidelity. When we map the CMB with satellites like Planck or WMAP, we are not looking at a picture of the early universe. We are effectively looking at the early universe. The photons striking our detectors have been traveling for almost the entire age of the cosmos, carrying with them an imprint of the conditions at the surface of last scattering, that moment of transition. This creates a breathtaking weave of past and present. We are receiving information in our now that was encoded in the universe's then, making the CMB the ultimate time machine, allowing us to directly observe the primordial past. The most astonishing revelations, however, lie not in the uniformity of this background hum, but in its tiny, exquisite imperfections. The CMB is not perfectly smooth. It contains minute temperature fluctuations, anisotropies, variations on the order of 1 part in 100,000. These tiny ripples are the cosmic seeds from which the entire large-scale structure of the universe grew. They are the gravitational blueprints for galaxy clusters, filaments, and voids. But some cosmologists believe these patterns might hold an even deeper secret, potential evidence for a universe that existed before our Big Bang, or for a cosmos where time is not linear but cyclical. Certain large-scale anomalies in the CMB, like the mysterious cold spot or unexpected alignments in the polarization of the light, are difficult to explain with our standard model of inflation. Some theories, like conformal cyclic cosmology proposed by Roger Penrose, suggest these could be imprints of gravitational waves from a previous eon, a prior universe that collapsed and then rebounded in a new Big Bang. In this view, time is not a line with a single beginning, but an endless cycle of expansion and contraction, with information from one epoch subtly encoded into the next, weaving time into an infinite, repeating loop. Furthermore, the precise statistics of these temperature fluctuations are our most powerful test for the theory of cosmic inflation, that period of exponential expansion in the first fraction of a second. The patterns we see are exactly what most inflationary models predict, offering strong support for the idea that the universe underwent this incredible growth spurt. This ties directly back to the nature of time, as inflation is thought to be the mechanism that established the arrow of time we experience today, stretching quantum fluctuations into cosmic scales and creating the initial conditions of low entropy from which time's arrow could emerge and flow. By studying the CMB, we are not just looking at a baby picture of the cosmos. We are investigating the very moment when the tapestry of time was first stretched on its loom, searching for clues about how its threads were initially spun. This ancient light, therefore, is our most direct link to the origin of time itself, a silent witness to the moment when the universe began to keep time. From the violent, tangible extremes of Magnetars and the ancient whisper of the cosmic microwave background, we now journey into a realm that is no less profound but exists in a domain beyond any map. This is not a place you can point a telescope toward, but a fundamental behavior of reality itself, operating beneath the surface of our everyday experience. We are entering the quantum entanglement realm, a phenomenon so bizarre that it challenges the very core of our classical understanding of space, time, and the nature of connection. Here, the universe reveals a layer where particles can share a bond that seems to laugh at the vast distances between them, suggesting that the tapestry of reality is woven with threads that ignore the conventional rules of separation and sequence. To grasp the sheer strangeness of entanglement, consider a simple, if imaginary, experiment. Imagine you have a special pair of gloves, one left-handed and one right-handed. You place each glove into an identical, perfectly sealed box without looking. You then take one box and travel to the farthest star in the Andromeda galaxy, over 2 million light-years away. Upon arrival, you open your box and find a left-handed glove. Instantly, you know with absolute certainty that the box back on Earth contains the right-handed glove. This is a classical correlation. The information was set the moment the boxes were sealed. Your act of observation didn't change the glove, it merely revealed a pre-existing state. Now replace the gloves with a pair of entangled particles, say 2 electrons. These particles are created together in a way that links a specific property, like their spin, a kind of intrinsic quantum rotation. According to the rules of quantum mechanics, until they are measured, these particles do not have a definite spin. They exist in a fuzzy superposition of possibilities, simultaneously spinning both up and down. They are shipped off to opposite ends of the universe, just like the boxes. When a scientist on Earth finally measures one electron and finds its spin is up, the other electron, instantly and regardless of the immense distance separating them, snaps into a state of spinning down. This is the quantum magic. It's not that the particles had a predetermined state that was simply revealed. the act of measurement on one particle actively and immediately determines the state of its partner, collapsing the shared wave function of the entire system in a single, non-local event. This spooky action at a distance, as Einstein famously derided it, presents a direct challenge to our classical notion of time and causality. In our everyday world, information and influence cannot travel faster than the speed of light. This cosmic speed limit is a cornerstone of relativity, and it ensures that cause always precedes effect, preserving a sensible timeline. But entanglement appears to violate this principle. The correlation between the particles is instantaneous. There is no time delay for a signal to travel from one to the other. This implies a kind of connection that operates outside of spacetime as we know it, a woven temporal link that suggests the particles are not truly separate entities but remain parts of a single, unified quantum system, no matter how far apart they are pulled. In this realm, time does not seem to mediate the interaction. The connection is primordial and immediate, existing in a domain where space and time are not the primary stage, but may themselves be emergent properties from a deeper, more interconnected reality. This profound weirdness forces physicists to confront deep interpretive questions about what is actually happening. One compelling explanation is the many worlds interpretation. In this view, the moment the measurement is made, the universe doesn't choose one outcome. Instead, it splits into multiple branches. In one universe, you measure spin up and your partner measures spin down. In another parallel universe, you measure spin down and your partner measures spin up. Both outcomes occur, but in separate, non-communicating timelines. From this perspective, entanglement isn't about spooky communication. It's about the correlation between different branches of reality. The particles aren't sending a signal. They are forever linked because their fates are woven together across the sprawling multiverse. This interpretation preserves locality. No faster-than-light signals are needed, but at the cost of an infinitely branching cosmos, suggesting that every quantum event weaves new threads into an ever-expanding tapestry of parallel existences. Beyond its philosophical implications, entanglement is the beating heart of the second quantum revolution, powering transformative technologies like quantum computing and quantum cryptography. A quantum computer doesn't use bits that are either 0 or 1. It uses quantum bits or qubits which can be 0, 1, or both at the same time, a superposition. But the real power comes from linking these qubits together through entanglement. When qubits are entangled, the manipulation of one directly affects the state of all the others in the group. This allows a quantum computer to perform a vast number of calculations simultaneously, exploring many possible solutions to a problem in parallel. It's a form of processing that doesn't just do math faster. It does math in a completely different dimension, one where the interconnectedness of the quantum realm is harnessed to solve problems that would take classical computers longer than the age of the universe to crack. Similarly, quantum cryptography uses the principles of entanglement to create communication channels that are theoretically unhackable. If two parties share a set of entangled particles, they can generate a secret, random key. Any attempt by an eavesdropper to measure the particles and intercept the key would immediately disturb their delicate quantum state, irrevocably altering the correlation and alerting the legitimate users to the presence of an intruder. This technology leverages the fundamental nature of quantum measurement that observing a system changes it to create a perfect seal of privacy, a direct application of quantum spookiness to the practical need for security. Exploring the realm of quantum entanglement ultimately forces us to reconsider the primacy of space and time. We are conditioned to see the universe as a collection of objects located in positions, with events unfolding in a clear temporal order. Entanglement reveals a layer of reality where this view is incomplete. Here, relationships and correlations are the fundamental entities. The universe seems to care less about where things are or when they are measured, and more about how they are connected. It suggests that what we perceive as separate particles are, in a deep and meaningful way, still a single, unified whole, their identities woven together by a connection that transcends the spatial and temporal boundaries we hold so dear. This is not a quirk of a few exotic particles. It is a foundational feature of the quantum world, pointing toward a cosmos that is far more deeply interconnected and far more mysterious than our classical senses could ever perceive. Yet if the strange, non-local connections of quantum entanglement suggest that our reality is more deeply unified than it appears, our next destination proposes an even more radical idea that the universe we perceive might be nothing more than a projection, a cosmic illusion painted on a distant, lower-dimensional canvas. We are venturing to the boundary defined by the holographic principle, a concept so profound it inverts our entire understanding of reality, suggesting that space, time, and even gravity itself are not fundamental but emergent, like a three-dimensional movie projected from a two-dimensional screen. This isn't science fiction. It's a serious theoretical framework born from the most puzzling paradox in physics, and it suggests that time itself is woven not from the fabric of space-time, but from the flow of information. The seeds of this incredible idea were planted not in the study of illusions, but in the hard thermodynamics of black holes. When Jacob Bekenstein and Stephen Hawking discovered that a black hole has entropy, a measure of its hidden information, and that this entropy is proportional not to its volume, but to the surface area of its event horizon, it sent shockwaves through the physics community. It implied that all the information describing everything that ever fell into a black hole, every star, every planet, every book ever written, is somehow encoded on its two-dimensional surface, not stored within its three-dimensional volume. The holographic principle takes this stunning revelation and applies it to the entire universe. It proposes that our entire three-dimensional cosmic experience, with its galaxies, stars, and people, is like a hologram. All the information needed to describe everything within a volume of space can be perfectly encoded on its two-dimensional boundary, like a cosmic DVD containing the complete data for an immersive 3D world. This leads to a breathtaking inversion of reality. In this view, the boundary is not the edge of something, it is the source of everything. The three-dimensional world we live in, with its depth and substance, is emergent. It is not the primary reality. The true, fundamental description of the universe exists on a distant, lower-dimensional surface. This means that familiar concepts like location and distance might be derived approximate notions. Two objects that appear far apart in the 3D projection might be described by bits of information that are neighbors on the 2D boundary. Space itself is not a fundamental stage, but a consequence of how information is organized and processed on this underlying surface. The most developed and powerful example of this principle at work is the anti-de Sitter/conformal field theory correspondence, or AD/S/CFT. This is a concrete mathematical duality, a kind of dictionary proposed by physicist Juan Maldacena. It states that a theory of gravity operating in a certain kind of negatively curved five-dimensional spacetime, the bulk, is completely equivalent to a quantum field theory without gravity operating on its four-dimensional boundary. In simpler terms, this means that the messy, complicated physics of gravity and black holes in a higher dimensional world can be perfectly translated into the well-understood physics of particles and quantum forces on a lower dimensional surface. A calculation that is impossibly difficult in the gravity theory might be straightforward in the quantum theory, and vice versa. This isn't just a nifty trick. It is a profound clue that gravity itself might be an emergent phenomenon, a force that arises from the collective behavior of quantum information on the boundary, much like the force of temperature emerges from the collective motion of molecules. Now consider the staggering implication this has for the nature of time. In the boundary quantum field theory, time is just a parameter, a coordinate that labels the evolution of quantum states. But in the emergent bulk, the world we perceive time becomes a dimension we move through, a river we feel flowing. The holographic principle suggests that our entire experience of linear, continuous time is an illusion that arises from how information is processed and updated on the boundary. Time's flow might be analogous to a movie. A DVD is a two-dimensional object with static data encoded in concentric rings. Yet, when played, it generates the illusion of a flowing, three-dimensional narrative with a clear past, present, and future. In the same way, the boundary might hold a static encoding of all events, and our perception of time is simply the process of this information being read or rendered into the dynamic experience we call reality. This challenges the very core of what time is, suggesting it is not a fundamental ingredient of the universe but a derived property, an emergent narrative woven from the way information interacts. This perspective also hints that time might not be continuous at its most fundamental level. Just as a digital movie is made of discrete frames, the process on the boundary might operate in discrete, fundamental steps. Time could advance in tiny, indivisible quanta, a concept that aligns with theories like loop quantum gravity. Our smooth experience of its flow would then be a macroscopic approximation, much like a spinning wheel appears as a continuous blur even though it is made of discrete spokes. The holographic boundary, therefore, represents the ultimate frontier of our understanding. It is a place where the very nature of time shifts from being a continuous dimension to being a relational or computational property, a derivative of the dynamics of information. It forces us to consider that the rich tapestry of our temporal experience, the memories we cherish, the future we anticipate, might be the magnificent output of a cosmic calculation happening on a distant, lower-dimensional screen, a profound mystery that redefines not only what time is, but what we are. But if the holographic principle suggests our reality is a projection from a distant boundary, our next journey takes us to a far more tangible, yet equally unsettling, destiny for the entire cosmos. We are fast-forwarding trillions of years into the future, to a time when the universe as we know it has been utterly transformed by its most mysterious component, dark energy. This is the dark energy-dominated era, a phase that represents not just a change in the universe's contents, but a fundamental shift in the very nature of time and connectivity, leading us toward a future of profound isolation and silence. To understand this era, we must first grapple with the force that defines it. Dark energy is not a substance in the traditional sense. It is a property of space itself, a kind of anti-gravity that causes the universe's expansion to accelerate. Discovered in the late 1990s through observations of distant supernova, its existence was a monumental shock that overturned the long-held assumption that the universe's expansion was slowing down. Instead, we learned that a mysterious repulsive force is steadily pushing galaxies apart at an ever-increasing rate. In the grand cosmic tug of war between gravity, which pulls things together, and dark energy, which pushes them apart, dark energy is winning. And its victory will have consequences that rewrite the rules of reality on the largest scales imaginable. As this acceleration continues unabated, the universe will undergo a dramatic and irreversible transformation. Galaxies that are currently visible to us will begin to recede faster and faster. Their light, already redshifted, will be stretched to longer and longer wavelengths, eventually shifting beyond the detectable range of any conceivable instrument. One by one, galaxies outside our own local group will vanish from our sky, their light becoming too faint and too redshifted to ever see again. The universe will not contract or collapse. It will simply fade away, leaving our galaxy and its immediate neighbors utterly alone in a vast and expanding void of darkness. The observable universe, the sphere of everything we can possibly know about, will shrink dramatically, isolating any future civilizations in an island universe with no external landmarks, no new information from beyond, and no way of ever knowing that a larger cosmos once existed. This cosmic isolation has a direct and chilling impact on the nature of time itself. In our current universe, we can synchronize clocks across vast distances by observing the same cosmic events. We share a common, albeit relativistic, timeline with distant galaxies, but in the dark energy-dominated era, as galaxies become causally disconnected, moving beyond each other's light cones, this shared timeline shatters. Different regions of space will become their own separate universes, each evolving along its own independent timeline with no way to communicate or compare. Time, which we experience as a universal constant, will become utterly relative and ultimately meaningless on a cosmic scale. There will be no now that encompasses the cosmos, only countless isolated nows disconnected from one another forever. The universe's tapestry of time won't just be woven. It will be cut into countless separate pieces, each fraying at the edges into nothingness. This bleak, lonely endgame is what cosmologists call the heat death, though it's less a dramatic explosion and more a slow, inexorable descent into maximum entropy. As the universe expands and matter becomes more and more diffuse, the energy gradients that power stars, galaxies, and life itself will gradually smooth out. All the usable energy in the universe will eventually be converted into a uniform, lukewarm sea of photons and elementary particles, a state of equilibrium where no work can be done and no change can occur. In this final state, the concept of time loses all meaning. Time's arrow is defined by the increase of disorder, the movement from low entropy to high entropy. But once maximum entropy is reached and no further change is possible, the arrow of time effectively vanishes. There is no past or future, only a static, eternal present. The universe will have reached its final, timeless state. Studying this far future era is not merely an exercise in cosmic melancholia. It is essential for understanding the deep connection between time, gravity, and the universe's evolution. The fact that the universe started in a state of incredibly low entropy, a highly ordered, dense state, is the very reason we have an arrow of time at all. The future dominated by dark energy represents the other end of that spectrum, the highest possible entropy state. By modeling this future, cosmologists are essentially tracing the life story of time itself, from its explosive birth in the low entropy Big Bang to its eventual dissolution in the high entropy heat death. It shows us that time is not a separate, abstract dimension, but is intimately woven into the content and evolution of the universe. It is a dynamic participant in the cosmic story, one whose very nature is dictated by the amount and distribution of matter and energy. This invites a profound philosophical reflection. Our entire existence, our history, our consciousness, all take place during a relatively brief cosmic golden age, a window of time between the initial fireball and the eventual freeze, when the universe is structured enough for complexity to arise but has not yet been smoothed into oblivion by expansion. We are living in a special time, a transient era where the cosmos is alive with structure and change. The dark energy-dominated era reminds us that time is not a given. It is a condition, a phase of the universe that had a beginning and, according to our best models, will have an end. It forces us to see our place in the cosmos not as a permanent fixture, but as a fleeting moment of awareness in a vast and evolving tapestry that is still being woven. A tapestry whose final threads are being drawn toward a silent and timeless conclusion. But to witness quantum strangeness on a truly grand scale, we don't always need to look to the cosmos. Some of the most profound insights into the nature of time are now being uncovered in a laboratory that floats 250 miles above the Earth, the International Space Station. Here, in the serene microgravity of orbit, scientists are creating and studying one of the most exotic states of matter ever achieved, the Bose-Einstein condensate. This isn't a place you can find in nature. It is a state of matter engineered by human ingenuity, a cloud of atoms cooled to a temperature a mere whisper above absolute zero, the point where all classical motion ceases. At this extreme cold, something magical happens. Individual atoms lose their identities, their quantum waves spreading out and overlapping until they sync up into a single, collective superatom, a macroscopic entity that behaves as one giant quantum particle. This is a realm where the bizarre rules of the quantum world, typically hidden in the subatomic shadows, are blown up to a scale we can directly observe and manipulate. The challenge with studying these condensates on Earth is gravity. That relentless force pulls on the fragile cloud, causing it to sag and distort, and it must be held in place by magnetic traps that themselves interfere with the delicate quantum states researchers want to observe. This is why the ISS has become the ultimate laboratory for this work. In the continuous free fall of orbit, gravity's pull is cancelled out, creating a near-perfect microgravity environment. Here, a Bose-Einstein condensate can be formed and then released, where it will simply float, untethered and unaffected, for much longer periods than would ever be possible on the ground. This allows scientists to observe its behavior with unparalleled precision, watching the quantum ballet unfold in slow motion and with perfect clarity. Facilities like NASA's Cold Atom Lab are pioneering this research, turning the space station into a factory for generating these ultra-cold quantum gases, pushing the boundaries of how cold we can make matter and how long we can preserve its quantum coherence. Within these floating clouds of super-cold matter, physicists are probing the very intersection of quantum mechanics and gravity, a frontier known as quantum gravity. One of the key experiments involves studying wave packets in the condensate, essentially giving the cloud a gentle nudge and watching how its quantum wave function evolves and spreads out over time. In the microgravity of space, this evolution can be observed with minimal interference, providing a pristine testbed for fundamental theories. Even more intriguing is the use of these condensates as exquisitely sensitive sensors for forces like gravity and rotation. Because the entire condensate acts as a single quantum object, it is incredibly susceptible to the slightest environmental changes. A passing gravitational wave, for instance, would ever so slightly ripple the fabric of spacetime, and that minuscule distortion could potentially be detected by a change in the condensate's quantum state. This turns the Bose-Einstein condensate into a canary in the coal mine for the subtlest forces in the universe, a tool for listening to the faint whispers of spacetime itself. This research also offers a unique window into how time might behave in such a coherent quantum system. In a Bose-Einstein condensate, the concept of a single particle having a well-defined trajectory breaks down. The atoms are delocalized and entangled, existing in a shared state across the entire cloud. In such a system, the flow of time might not be experienced in the simple, linear way we are accustomed to. Some theories suggest that under these conditions of extreme quantum coherence, time could emerge from the correlations between particles, appearing to flow as a collective property of the system rather than an external parameter. It's a glimpse into the possibility that time itself is not a fundamental background field but an emergent phenomenon that arises from quantum relationships, a concept that resonates with theories of quantum gravity. By creating and studying these coherent quantum states in the quiet of space, we are essentially running experiments on the origin of temporal experience itself, testing how complexity and correlation can give rise to the illusion of a flowing time. What makes this 20th entry on our list so remarkable is its accessibility. The other locations we have explored, black holes, neutron stars, the edge of the cosmos, are distant, hostile, and impossible for us to visit or manipulate. They are subjects for observation and theory, but the Bose-Einstein condensate is different. It is a wonder we have built with our own hands, a pocket of extreme quantum reality that we can create, control, and experiment on at will. It represents a magnificent bridge between the esoteric world of theoretical physics and the tangible world of experimental science. It demonstrates that the weaving of time is not a mystery locked away in the far reaches of the universe, but a fundamental process that can be investigated in a lab, even if that lab is orbiting our planet. The work aboard the ISS is quietly revolutionizing our understanding, showing that the keys to unlocking the deepest secrets of time and space might not only be found by looking outward, but also by looking inward into the coldest and most ordered states of matter we can possibly create. But if the delicate quantum states aboard the space station represent a fragile, human-made window into time's mysteries, our next destination plunges us back into the realm of pure thought experiment, to a conceptual space that has fueled scientific debate and science fiction for generations. We are entering the grandfather paradox resolution zone, a place that doesn't exist on any map but lives at the fiery intersection of logic, physics, and imagination. This is the ultimate puzzle of time travel. What happens if you go back in time and prevent your own existence? The very question seems to tie causality into a knot, threatening to unravel the logical consistency of the entire universe. Yet, this apparent dead end is not where the story ends. It is where some of the most fascinating physics begins, proposing mechanisms that would allow the universe to weave its way out of the paradox, preserving a rational reality. The classic formulation is simple, brutal, and deeply unsettling. Imagine you build a time machine, travel to a time before your grandfather had children, and accidentally or intentionally cause his death. This act would prevent one of your parents from being born, which would, in turn, prevent you from being born. But if you were never born, you could never have built the time machine or taken the journey to kill your grandfather. So he would have lived, your parent would have been born, you would have been born, and you would have traveled back and killed him. This creates an endless, self-negating loop of cause and effect with no stable outcome. A logical contradiction that seems to make time travel to the past an impossible fantasy. For decades, this paradox was considered the ultimate veto against backward time travel. But modern physics, in its relentless creativity, has begun to propose ways the universe might resolve such inconsistencies on its own, without breaking its own rules. The most prominent and compelling solution comes from the many worlds interpretation of quantum mechanics. In this view, championed by physicists like David Deutsch, every quantum event that has multiple possible outcomes doesn't just result in one outcome. It results in all of them, each unfolding in a new, parallel universe. The timeline doesn't have a single history. It has a constantly branching tree of every possible history. Apply this to time travel, and the grandfather paradox simply evaporates. When you step into your time machine and set the coordinates for the past, you are not traveling back within your own timeline. You are journeying to a parallel universe, one that is nearly identical to yours up to the moment you arrive. In this new branch of reality, your actions create a new future. If you prevent your grandfather from having children, you simply create a timeline where you never exist. But your original timeline remains untouched and paradox-free. You came from there, and your actions in the new branch have no effect on it. The time traveler isn't a murderer of their own history. They are an immigrant from one reality to another, and their actions weave a new, self-consistent thread into the vast tapestry of the multiverse. This breathtaking idea transforms time from a single, linear thread into a multivalent entity, a sprawling web of possibilities. The grandfather paradox resolution zone, then, is not a location in spacetime but a condition, a set of physical laws that would allow for the branching of worlds to accommodate non-linear causality. It represents a universe so robust and clever that it can absorb any paradoxical action and simply spin off a new reality to house it, ensuring that every timeline remains logically sound within itself. This doesn't just solve the grandfather paradox, it potentially resolves any time travel inconsistency, from killing a butterfly and altering the future to giving Shakespeare a copy of his own complete works. Every action creates its own new world, weaving an infinite number of alternate histories. Other, more speculative theories offer different resolutions. The idea of a self-healing timeline or a principle of cosmic censorship suggests that the universe might simply not allow paradoxical events to occur. The moment you raise the weapon to your grandfather, a quantum fluctuation might cause the gun to jam, or a sudden gust of wind might knock you off balance. The universe would employ any means necessary to prevent the logical inconsistency, enforcing a kind of physics police that ensures all events remain self-consistent. Another idea posits that time travel to the past might only be possible to observe, not to interact with. You could be a ghost in the past, unable to change anything you see. While these ideas are less developed than the many worlds approach, they all point toward a universe that possesses a deep-seated preference for consistency, finding elegant ways to weave even the most disruptive actions into a coherent whole. Exploring this conceptual zone is far more than a fun, intellectual exercise. It forces us to confront the very nature of causality and reality. Is the universe a single, predetermined story, or is it a garden of forking paths? Does it value the consistency of a single timeline over the proliferation of infinite ones? The grandfather paradox pushes our understanding of physics to its absolute limit, probing the boundary between the possible and the impossible. It shows us that the flow of time we experience might be just one current in a much wider river of reality, and that the universe's methods for preserving order are far more sophisticated and wondrous than we could have ever imagined. But to understand the true origin of the cosmic tapestry we've been exploring, we must journey back to the very beginning of beginnings, to a moment so fleeting and so far beyond our everyday experience that it exists at the very limits of what physics can describe. We are venturing into the Planck epoch, the first 10 million trillionths of a second after the Big Bang. To call this a moment is a profound understatement. It is the foundational quantum tick of the cosmic clock, a duration so short that within it, the very concepts of time and space as we know them cease to have any clear meaning. This is not merely the early universe. This is the universe in its raw, unformed, and most primordial state, a domain where the threads of reality were first spun on the loom of existence. During this incomprehensibly brief era, the energy and density of the cosmos were so extreme that the four fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces were fused into a single, unified superforce. The universe was smaller than a single subatomic particle, yet it contained the seed of everything we see today. In this seething, energetic foam, the distinctions we rely on to make sense of reality completely break down. Matter and energy were interchangeable, particles and forces were one and the same, and crucially, the smooth, continuous fabric of spacetime described by Einstein's relativity could not hold. Instead, it was likely quantized, broken into the tiniest possible grains of space and the briefest possible moments of time. This is the realm of the Planck length and the Planck time, the absolute smallest scales at which our current laws of physics can even attempt to operate. To venture any further back is to enter a territory of pure speculation, a place where our mathematics fails and our language has no words. Within this chaotic, frothing quantum foam, the very idea of a linear arrow of time becomes meaningless. Our entire experience of cause and effect, of a clear progression from past to present to future, relies on a universe with a defined structure and increasing entropy. But in the Planck epoch, there was no structure, there was no clear past or future. The concepts of before and after simply did not apply, as time itself was not a smooth flowing river but a turbulent, boiling pot where events flickered in and out of existence without sequence or order. This was the ultimate state of woven time, a primordial knot where all of spacetime's threads were tangled together in a single, inseparable whole. It was a reality without chronology, a canvas without a frame, existing in a state of pure, undifferentiated potential where anything that was possible could and did happen. Modern theories of quantum gravity, such as loop quantum cosmology, offer a fascinating glimpse into how this era might have unfolded without the terrifying infinities of a classic Big Bang singularity. Instead of a universe exploding from an infinitely dense point, this theory proposes a big bounce. In this model, our universe is not the first but the latest in a potentially endless cycle. A previous universe may have contracted under its own gravity, but instead of collapsing into a singularity, the repulsive force of quantum gravity would have kicked in at the Planck density, causing a rebound, a bounce that gave birth to our own expanding cosmos. This breathtaking idea suggests that the Planck epoch was not an absolute beginning, but a transformative gateway, a cosmic reset point where the laws of physics were reborn. In this view, the arrow of time might not have started at the bounce but could have been reversed or reoriented, meaning our entire cosmic history could be just one phase in an eternal cycle of expansion and contraction, with time itself being rewoven at every turn. Studying this elusive epoch is not just an academic pursuit of the absolute beginning, it is the fundamental quest to understand the origin of time itself. The smooth, linear, relativistic time we experience today, with its clear arrow and reliable rhythm, had to emerge from this initial chaos. It is a property that was not present at the start, but one that crystallized as the universe cooled and the forces of nature separated from their unified state. The transition from the timeless quantum foam of the Planck era to the structured spacetime we inhabit is the most profound phase change in all of existence. It marks the moment the cosmic loom began its work, untangling the threads of time and space and setting them on their respective paths, weaving the ordered tapestry of cause and effect that would eventually allow for galaxies, planets, and conscious beings to arise and make sense of it all. Yet, even as we contemplate these profound mysteries at the edge of physics, one of the most humbling and beautiful truths is that the universe's most exotic phenomena are not confined to the distant cosmos. In fact, one of the clearest examples of woven spacetime is happening right here, right now, in the space around our own planet. We've journeyed to the ergosphere of a black hole, where frame dragging twists spacetime into a vortex, but a far more subtle version of this exact same effect is at work in Earth's vicinity, a ghostly whisper of general relativity that proves these cosmic laws are universal. This is the frame-dragging field, a minuscule but measurable distortion caused by our planet's rotation, and its detection stands as a monumental triumph of human precision and patience. The concept itself is breathtaking. A massive rotating object doesn't just create a gravitational well that pulls objects inward, it also drags the very fabric of spacetime around with it as it turns. Picture Earth not as a static ball sitting in space, but as a sphere spinning in a vast, invisible fluid, the fabric of spacetime itself. As it rotates, it creates a faint whirlpool in that fabric, a swirling current that tugs on anything nearby. This isn't a force in the traditional sense. It's a geometric effect, a warping of the coordinate grid of the universe itself. For a satellite in a carefully chosen orbit, this means its path is ever so slightly altered not just by Earth's mass, but by its spin. A gyroscope placed in such an orbit wouldn't just point in a fixed direction. Its axis of rotation would be ever so slowly dragged around by this invisible cosmic current. The predicted effect is tiny, a drift of just a few thousandths of a degree per year, but it is a direct prediction of Einstein's theory, a test that had to be passed. Proving this effect existed became a scientific quest that spanned decades, a story of perseverance against almost impossible odds. The mission designed to do it was Gravity Probe B, one of the most complex and precise experiments ever launched into space. The spacecraft itself was a technological marvel, containing the most perfect gyroscopes ever created, spheres of fused quartz so perfectly smooth that if they were scaled to the size of the Earth, their tallest mountains would be less than 3 meters high. These gyroscopes were chilled to near absolute zero and placed in a vacuum, floating in a state of near-perfect free fall, all to isolate them from any external influence except the subtle nudges of spacetime itself. The goal was to measure two effects: the much larger geodetic effect caused by the static warping of space by Earth's mass, and the far more elusive frame-dragging effect. For over a year, the spacecraft collected data and then began the painstaking, years-long process of analysis, teasing a signal of unimaginable faintness out of a sea of noise. The successful confirmation of frame dragging was a quiet revolution. It demonstrated that the dramatic space-time weaving we associate with black holes and neutron stars is not some exotic exception reserved for the most extreme environments. It is a universal phenomenon, a fundamental part of how mass and energy interact with the cosmos. Every rotating object, from a spinning star to a child's top, creates its own tiny frame-dragging field. Around Earth, the effect is vanishingly small, but it is there, a permanent, whispering vortex in time and space that our planet has been carving out through the eons. This means that right where you are sitting, the flow of time is ever so slightly different than it would be if Earth were stationary. The difference is infinitesimal, measured in billionths of a second over a human lifetime, but it is real. The universe is not a static stage. It is a dynamic, swirling fabric, and we are all constantly immersed in its subtle currents. This profound discovery does more than just confirm a century-old prediction. It fundamentally connects the cosmic to the local. It shows us that the same physical principles that govern the dance of galaxies and the fate of black holes are also operating in our own celestial backyard. The tools we use to detect it, incredible precision, patient observation, and a deep trust in the mathematical elegance of relativity, are the same tools we use to explore the farthest reaches of the universe. The frame-dragging field near Earth is a powerful reminder that the universe is not out there, separate from us. Its laws are written into the space around our own world, waiting for us to develop the sensitivity to read them. It invites us to see our planet not just as our home, but as a laboratory for the most profound physics, a place where the grand tapestry of spacetime is being woven on a human scale, offering a glimpse of the cosmic wonders that lie hidden in the fabric of our everyday reality. But perhaps the most profound puzzle of all emerging from this evaporation process is the question of what happens to information. In our everyday world, information seems sacred. If you burn a book, in principle, you could recover the information from the smoke and ashes by reversing all the physical processes. Quantum mechanics insists this principle must hold universally. Information cannot be truly destroyed, but a black hole presents a terrifying challenge to this rule. Everything that falls past the event horizon, every atom, every particle, every bit of data that made up a star, a planet, or a library, seems to be irretrievably lost to the singularity. Yet, Hawking's original calculation showed that the radiation leaking out is purely thermal, a featureless heat bath. It contains no information about what fell in. If the black hole evaporates completely, it appears that all that information has been erased from the universe forever. This is the infamous black hole information paradox, a direct conflict between the rules of quantum mechanics and the predictions of general relativity, and it suggests that our understanding of time and causality is deeply flawed at this quantum gravity interface. The resolution to this paradox is one of the most active and exciting areas of theoretical physics, and it forces us to reconsider the very nature of time during evaporation. One compelling idea is that the Hawking radiation is not truly random after all. As the black hole evaporates, subtle quantum correlations might form between the radiation particles escaping at different times. The information about what fell into the black hole could be encoded not in any single particle of radiation, but in the intricate pattern of relationships between all the emitted particles, like a cosmic Sudoku puzzle where the answer is hidden in the global connections, not in any individual number. This process would be incredibly complex, involving a phenomenon known as quantum entanglement on a massive scale. The interior of the black hole and the exterior radiation would become profoundly entangled, and as the evaporation proceeds, this entanglement would transfer the information back out into the universe in a highly scrambled but recoverable form. In this view, time during evaporation isn't linear. It's a process of quantum decoding where the history of the black hole's contents is slowly and meticulously woven back into the fabric of the external universe. This leads to an even more radical possibility, a form of time reversal at the quantum level. Some theories suggest that to preserve information, the laws of physics must behave in a time-symmetric way, even during the extreme process of black hole evaporation. This doesn't mean events literally run backwards, but that the underlying quantum description of the process looks the same whether you run the clock forward or backward. The final state of complete evaporation would have to be intricately connected to the initial state of the black hole's formation, with the information taking a roundabout path through the quantum foam to re-emerge. This idea pushes us to think of time not as a simple flow, but as a more complex web of correlations and connections that can preserve causality and information in ways that defy our classical intuition. The evaporation process becomes a grand demonstration of how quantum mechanics can weave time into a tapestry that is consistent and complete, even when gravity tries to tear it apart. The implications of this extend far beyond black holes. They strike at the heart of our quest for a unified theory of physics. The quantum gravity interface during evaporation is the ultimate testing ground for theories like string theory and loop quantum gravity. String theory, for instance, has made progress by modeling black holes not as infinitely dense points, but as fuzzy bundles of strings and brains's multidimensional objects whose properties can be calculated. In some string theory models, the information capacity of a black hole is precisely accounted for by the states of these fundamental strings, and the evaporation process can be described without any loss of information, neatly resolving the paradox. Loop quantum gravity, with its granular picture of spacetime, also avoids the singularity and provides a framework where information can be preserved through the evaporation process. By studying this delicate interface, these competing theories are not just solving a puzzle about black holes, they are providing crucial clues about how to stitch together the quantum world and the gravitational world into a single, coherent description of reality. The way time operates at this frontier, whether it remains linear, becomes emergent, or exhibits subtle quantum reversibility, will be a key signature of the correct theory, guiding us toward a final understanding of the universe's most fundamental law. And now we arrive at the final destination on our cosmic tour, a concept that stretches the imagination to its absolute breaking point and forces us to reconsider the very definition of reality. We are looking beyond the limits of our own universe to the theoretical frontier that separates our cosmic bubble from all others, the multiverse cosmological horizon. This isn't a physical boundary we could ever hope to cross. It is the ultimate veil, the dividing line between our universe with its specific set of physical laws and the possibility of countless other universes existing alongside it, each with its own utterly unique and potentially alien version of reality. Here, the idea of woven time expands from a curious feature of our cosmos into a fundamental principle of a possibly infinite meta-reality, where time itself might not be a single thread but a boundless spectrum of temporal fabrics. The journey to this mind-bending idea often starts with the theory of cosmic inflation. We've already explored how our universe likely underwent a period of exponential expansion in its first moments. But many leading cosmologists like Alexander Vilenkin and Andrei Lind suggest this inflationary process might not be a one-time event. Instead, it could be eternal. Picture a vast, bubbling cosmic foam where the high-energy state of inflation is the default. Within this frothing meta-universe, random quantum fluctuations continuously cause tiny bubbles to nucleate and inflate at an incredible rate. Each of these bubbles is a separate universe, pinching off from the inflationary background and developing its own distinct local laws of physics as it cools. Our entire cosmos, with its hundreds of billions of galaxies, would be just one bubble in this infinite, ever-growing foam of universes, a single brick in a wall that stretches on forever. This is where the nature of time becomes truly unshackled. Within our bubble, we experience a very specific kind of time, a one-way arrow that points from a low-entropy Big Bang toward a high-entropy future. This directionality is deeply woven into everything we do, from remembering the past to anticipating the future. But there is no fundamental law of physics that says time must flow in this direction. It's simply a consequence of our universe's particular initial conditions. In another bubble universe with different starting parameters, the arrow of time could point in the opposite direction. Beings in that universe would perceive a world where cause and effect are reversed. They might remember the future and anticipate the past. In another bubble, time might not have a clear arrow at all, existing in a state of eternal, chaotic fluctuation where the concepts of before and after are meaningless. And in some universes, as proposed by physicists like Max Tegmark, the very dimensionality of time could be different. Our reality has 3 spatial dimensions and 1 time dimension. But another universe could have 2 time dimensions and 2 spatial dimensions, a reality where the flow of time wouldn't be a river but a vast, complex plane, with history unfolding across multiple temporal axes in ways we cannot possibly visualize. The most dramatic temporal weaving could occur at the boundaries where these bubble universes interact. While the inflating space between bubbles usually keeps them forever separate, in an eternal multiverse, collisions are not just possible, they might be inevitable. Imagine two bubble universes, each with its own arrow of time, expanding on a collision course. Where their cosmological horizons meet and briefly merge, the laws of physics from each universe would clash in a cataclysmic event of unimaginable energy. In this violent interaction zone, time would not simply stop or flow in one direction. It could become braided, with the temporal rules of one universe temporarily influencing the other. Causality could become profoundly mixed, creating a region where effects might precede causes from one perspective while following them from another. These collisions could potentially leave permanent scars on the fabric of each universe. Some cosmologists even search for evidence of these ancient crashes in the subtle patterns of our own cosmic microwave background, looking for strange, circular imprints that would be the bruises from a long-ago impact with a neighboring cosmos. Contemplating the multiverse horizon is ultimately a lesson in cosmic humility. It challenges the deeply ingrained assumption that our experience of time is the universal standard, the default setting for reality. Instead, it suggests that our linear, one-way temporal flow is merely a local bylaw, a rule that applies only within the confines of our particular cosmic bubble. Beyond our horizon, the possibilities are truly infinite. There could be universes where time is cyclical, ending in a big crunch only to be reborn in a new Big Bang in an endless cycle. There could be static universes where time does not pass at all, frozen in a single, eternal moment. Or there could be universes where time is emergent and granular, only appearing smooth and continuous from a large-scale perspective, much like a digital image appears smooth until you zoom in to see the pixels. This transforms time from a fundamental constant into a flexible, contingent property, a feature that is woven into the specific history and structure of each individual universe. This idea doesn't just change how we see the cosmos, it redefines our place within it. We are not just living in a universe, we are living in one that has a very specific and perhaps very rare kind of time, a time that allows for memory, for evolution, for history, and for consciousness to arise. The fact that we perceive a consistent, linear flow of time may be no more significant than the fact that we live on a planet with liquid water and a breathable atmosphere. It's not a necessary feature of existence, it's simply a feature of our existence, one that allowed us to come into being to observe it. The multiverse cosmological horizon is the final and most profound expression of woven time, revealing a meta-reality of breathtaking diversity where time is not one thing but everything, a grand, infinite tapestry of temporal experience, of which our own reality is but a single, beautifully intricate thread. We have traveled to the very edge of reality and back, exploring 25 cosmic locations where the ordinary flow of time simply doesn't apply. From the frozen moments at a black hole's event horizon to the seething chaos of the quantum foam, each destination has revealed a different facet of a universe where time is not a river, but a tapestry intricately woven by the fundamental forces of nature. This journey has shown us that gravity can stretch time into near eternity, that quantum mechanics can entangle moments across vast distances, and that the very structure of the cosmos can twist causality into loops. These are not abstract mathematical curiosities. They are the active, dynamic principles shaping everything from the smallest particles to the largest galactic clusters, proving that our classical view of a linear, universal clock is a comfortable illusion, a local phenomenon in a much grander and more mysterious reality. What makes this exploration so profoundly important is how it reshapes our most fundamental questions about existence. If time can be woven, looped, and even reversed in certain conditions, what does that mean for concepts like free will, destiny, and the nature of consciousness itself? Our entire experience of life is built upon the unshakable foundation of past, present, and future, yet the universe seems to operate on a canvas where these distinctions are not absolute. This doesn't just challenge physicists, it invites philosophers, artists, and every curious mind to reconsider our place in the cosmos. We are not merely living in time, we are expressions of it, temporary patterns in a cosmic fabric that is far more complex and interconnected than we ever imagined. The true wonder is that we have developed the capacity to even perceive these mysteries, to use mathematics and observation to peer behind the curtain of our everyday experience and glimpse the magnificent loom on which reality is woven. As our understanding continues to evolve, each new discovery adds another thread to this grand design. Missions like the James Webb Space Telescope and the Laser Interferometer Space Antenna are not just collecting data, they are reading the subtle patterns in the cosmic tapestry, bringing us closer to a unified theory that might one day explain how gravity and quantum mechanics collaborate to create the flow of time we experience. This is an active, living field of science, and every breakthrough, from confirming frame dragging around Earth to detecting gravitational waves, tightens the weave of our comprehension. The journey is far from over, and the greatest revelations about time likely lie ahead of us, waiting in the depths of a black hole, the precision of a quantum computer, or the equations on a physicist's chalkboard. I would love to hear which of these 25 places captured your imagination the most. Was it the terrifying singularity at the heart of a black hole, or the spooky connectedness of quantum entanglement? Share your thoughts in the comments below. Let's continue this fascinating conversation together. If your mind feels expanded by this journey through woven time, please show your support by liking this video and subscribing to the channel for more deep dives into the universe's greatest mysteries. Where should we explore next? The nature of dark matter, the mysteries of other dimensions, or the search for life beyond Earth? Let me know what you'd like to see. Thank you for joining me on this incredible adventure. Until our next exploration, keep looking up, stay curious, and never stop questioning the nature of everything. It's easy to view these 25 cosmic wonders as abstract marvels, intellectual curiosities confined to the distant edges of reality. But the profound truth is that the weaving of time is not just a subject for telescopes and theoretical equations. It's a tangible force that already shapes our daily lives and promises to revolutionize our future. The very same physics that twists time into knots at the edge of a black hole is operating right here in your pocket, in the technology that guides you to your destination. Every time you use a GPS satellite to navigate, you are relying on a direct application of Einstein's relativity. Those satellites orbit high above Earth, where our planet's gravitational grip is slightly weaker. Because of this, time for their atomic clocks actually runs faster than it does for us on the surface, by about 45 millionths of a second per day. If the system's engineers didn't deliberately program this time dilation correction into the software, your navigation accuracy would drift by over 6 miles per day, rendering the entire system useless within minutes. Your phone's map is therefore a constant and practical validation of woven spacetime, a daily reminder that time is not absolute but is intimately shaped by gravity and motion. This is just the beginning. The strange quantum connections we explored, like entanglement, are the foundational bedrock of the next technological revolution. Quantum computers don't process information with simple ones and zeros. They use quantum bits or qubits, which can be in a state of superposition. both 1 and 0 simultaneously. But their real power is unleashed through entanglement, that spooky link that binds particles together across any distance. When qubits are entangled, manipulating one instantly affects its partner, allowing a quantum computer to explore a vast number of possible solutions to a problem all at once. This isn't just a faster way of computing, it's an entirely new form of information processing, one that could allow us to design new life-saving medicines by simulating molecular interactions with impossible precision, or break current encryption standards while creating new, unhackable quantum networks. These technologies are being built in labs around the world today, directly harnessing the non-local, woven nature of quantum reality to achieve what was once pure science fiction. And the quest to understand these mysteries is driving some of the most ambitious scientific missions in history. The recently launched James Webb Space Telescope is more than a successor to Hubble. It is a time machine peering back to the very first galaxies, studying the era of recombination to better understand how the initial conditions of the universe were set. By analyzing the faint glow of ancient atmospheres on distant exoplanets, it even searches for the building blocks of life, connecting the cosmic tapestry to our own biological story. Meanwhile, the upcoming Laser Interferometer Space Antenna, or LISA, will open an entirely new window onto the universe. This space-based gravitational wave observatory will consist of 3 spacecraft flying in a giant triangle, firing lasers between them. It is designed to detect the low-frequency ripples in spacetime caused by the mergers of supermassive black holes and the passage of cosmic strings. LISA will allow us to literally listen to the vibrations of the cosmic loom as it weaves, providing a direct soundtrack to the most violent and energetic events in the universe, and testing our theories of gravity in ways ground-based detectors never could. This relentless pursuit of knowledge does more than just advance technology. It fundamentally deepens our philosophical understanding of our place in the cosmos. Contemplating the holographic principle or the multiverse doesn't provide easy answers, but it expands the canvas of what is possible. It challenges our anthropocentric view that our experience of linear time is the universal standard, suggesting instead that it is a beautiful, local phenomenon that allowed complex beings like us to evolve and ask these very questions. This scientific journey is a deeply human one, driven by an insatiable curiosity to understand the fabric of which we are a part. Each discovery, from the confirmation of frame dragging around our own planet to the first detection of gravitational waves, adds a new thread to the grand tapestry of understanding, weaving together a more complete and awe-inspiring picture of reality. Supporting this exploration, whether through public interest, education, or funding, isn't just an investment in new gadgets. It is an investment in our collective story, a commitment to unraveling the deepest mysteries of existence and discovering our true role in this magnificent, woven